Hello there, and welcome to Physics with William, where curiosity settles in for the evening and the universe is allowed to unfold at a gentler pace. Tonight, we are drifting toward one of the strangest places modern science has ever tried to describe, a place so extreme that many of the ordinary rules we trust begin to wobble, bend, and in some cases stop being useful altogether. We're going to spend some quiet time with a question that has fascinated physicists, writers, dreamers, and anyone who has ever looked up at the night sky and wondered what sort of machinery might be hidden in the dark. What actually happens inside a black hole? Before we ease any farther into that mystery, I would love to know where you're listening from tonight and what sort of hour has found you. Is it late evening where you are, with the room finally going still after a long day? Is it very early, with the world not quite awake yet? Or perhaps you're somewhere in between, stealing a soft pocket of time for yourself while everything else carries on around you. It feels oddly appropriate, does it not, to begin a journey into black holes by asking where in the universe you happen to be, because these objects have a way of making location seem far less simple than it first appears. And if this quiet exploration brings you some calm, or keeps your thoughts company for a while, do consider giving the video a like, and perhaps subscribing as well. It helps this small corner of slow science find other people who might need a peaceful voice and a curious question at the end of the day. Though I should warn you, black holes do have a habit of making ordinary reality seem rather suspicious afterward. You may emerge from this with a slightly altered relationship to gravity, time, and the general trustworthiness of space. Now then, get comfortable, loosen the grip of the day a little, and let us approach this carefully, because black holes are often introduced with a kind of dramatic flourish. They're usually described as cosmic monsters, celestial vacuum cleaners, bottomless pits in the fabric of existence. And while I understand the temptation, those descriptions do not really help very much. A black hole is not a hole in the sense that a tunnel or cave is a hole. It is not an empty place waiting to swallow things with some malicious appetite. In a physical sense, it is better understood as a region where gravity has become so intense that once something crosses a certain boundary, leaving is no longer possible. Not even light, the swiftest thing we know, can get back out. That alone is enough to make the mind pause. Light is usually our final reassurance. If something exists, light from it reaches us. If an object is hot, glowing, reflecting, burning, or even quietly sitting under starlight, some form of light tells us it is there. A black hole breaks that ordinary relationship. It does not shine in the usual way. It does not reveal itself directly. It announces itself through consequences, through the motion of nearby stars, through hot gas spiraling around it, through violent jets and distorted light and space behaving in ways that only make sense if something immensely compact and powerful is present. It is rather like finding a creature in the dark by noticing that the furniture keeps moving whenever it passes through the room. The phrase inside a black hole is where everything becomes especially difficult, because physics is very good at describing what happens outside one, and still impressively capable near the boundary. But once we ask what truly happens inside, we begin to lean against the edges of what our current theories can do. That is part of what makes the subject so compelling. We are not exploring a finished museum exhibit with polished labels and clean answers. We are standing at the edge of something science can partially map and partially only infer. There are strong ideas, solid predictions, remarkable insights, and then there is a thickening region of uncertainty, where our best models start to disagree or fall silent. Still, uncertainty is not the same as ignorance. We do know quite a lot. We know how black holes can form. We know what kinds of black holes exist. We know that an event horizon marks the boundary beyond which return is impossible. We know that time and space behave in startling ways near such objects. We know that falling into one would not be a pleasant wellness retreat. And we know that somewhere deep in the story lies one of the greatest unresolved problems in physics, because general relativity, which describes gravity beautifully on large scales, and quantum mechanics, which describes the microscopic world with astonishing accuracy, do not yet fully cooperate when pushed into the interior of a black hole. It is one of those scientific situations where both of your smartest friends are brilliant individually and somehow unbearable together at dinner. To understand why the inside of a black hole is so strange, it helps to begin with something that seems almost ordinary by comparison: gravity itself. We tend to think of gravity as familiar because it is always with us. It keeps our feet on the ground, our oceans in place, and our coffee from floating gently across the kitchen. But familiarity can be misleading. Gravity is, in many ways, the most quietly extraordinary force in our daily lives. It sculpts planets and stars, governs orbits, bends light, and on the larger scales it helps determine the architecture of galaxies and the evolution of the universe. On Earth, gravity feels steady and modest, like a reliable stagehand doing its work without demanding applause. Around a black hole, that same stagehand has apparently joined a very intense powerlifting program. One of the reasons black holes feel so unsettling is that they take a simple idea and push it beyond all comfortable limits. Matter has gravity. More matter means stronger gravity. Compress enough matter into a sufficiently small region, and gravity becomes overwhelming. That is the broad path. But even that summary hides something important. A black hole is not only strong gravity. A star can have strong gravity. A planet can have strong gravity. The moon has gravity. A determined loaf of bread has gravity, though admittedly not enough to inconvenience anyone. The distinctive feature of a black hole is concentration. Mass packed into so little space that the geometry of space-time itself is radically altered. That phrase, space-time, is one we will spend time with, because it matters enormously here. According to Einstein, gravity is not best thought of as an invisible rope pulling objects toward one another. Instead, mass and energy shape the geometry of space and time, and objects move along that curved geometry. This is one of those ideas that can sound abstract until the consequences become concrete. Around the Earth, space-time is curved gently enough that you can live a normal life without noticing. Around a black hole, the curvature becomes so severe that paths that would once lead outward no longer do. The directions available to you narrow in a profound way. Beyond a certain boundary, every possible future points inward. That is already a very strange sentence, and it deserves to be handled slowly. We normally think of space as giving us options: left, right, forward, backward, up, down. If a place is dangerous, we can leave. If a room is unpleasant, there is usually a door. If a neighbourhood cat disapproves of our presence with sufficient commitment, retreat remains a sensible plan. Near and inside a black hole, this intuition begins to fail. At the event horizon, the point of no return, moving outward ceases to be a possible path in the ordinary sense. Not because you're too weak or because the black hole is actively grabbing you like an octopus with opinions, but because the structure of space-time has changed so drastically that outward no longer leads to escape. This is one reason black holes are so often misunderstood in popular culture. They are pictured as cosmic drains pulling everything toward a central opening. But if the sun were magically replaced by a black hole of the same mass, the Earth would not suddenly be slurped inward like a noodle. We would continue orbiting, though the loss of sunlight would certainly spoil the week. From a distance, gravity depends on mass, not on whether that mass is in the form of a star or a black hole. What makes black holes special is what happens when you come very close. The region near them is where space-time becomes so distorted that the familiar distinction between staying, leaving, and falling stops behaving the way common sense expects. Another reason the idea of going inside a black hole is so captivating is that the word inside implies an interior. We might one day describe the way we describe the inside of a cave, a submarine, or a very badly organised drawer. But the inside of a black hole is not an environment in the usual sense. It is not a hidden chamber with strange walls and eerie weather. It is not a dark room where matter piles up in recognisable forms. The deeper truth seems to be much more severe. The interior is a domain in which trajectories lead inward toward what general relativity predicts as a singularity, a place where density and curvature are driven beyond the limits of the theory. That does not necessarily mean nature really produces infinities in a literal sense. More likely, it means our description breaks down there, the map tears before the landscape ends, and yet before we rush too quickly to the centre, it is worth lingering on something more human. Why do black holes capture the imagination so effectively? Why do they appear in films, novels, thought experiments, jokes, headlines, and the occasional overconfident internet post that begins with someone saying they have fully solved the mystery using only common sense and a napkin? Part of the reason is that black holes press on several deep instincts at once. They are invisible yet real. They are simple in some ways and impossibly complex in others. They are mathematically elegant and emotionally unnerving. They represent a limit, and humans are very drawn to limits. The tallest mountain, the deepest ocean trench, the coldest place, the oldest fossil, the edge of the observable universe. Black holes feel like the limit of falling, the limit of concealment, the limit of what nature will allow matter and gravity to do before our understanding starts to slip. There is also something psychologically potent about a place from which information cannot easily return. We are creatures who rely on stories, signals, memory, and evidence. We like windows, we like traces, we like being able to ask, "What is it like there?" and receive some kind of report. A black hole withholds that report. It turns the universe into a one-way conversation. We can see matter approach. We can calculate what should happen. We can detect radiation from surrounding material. We can watch stars orbit an invisible center. But the interior itself refuses to send back postcards. It is the most stubbornly private object in astrophysics. That privacy has consequences, not only for imagination but for science itself. Some of the most important debates in modern physics revolve around whether information that falls into a black hole is truly lost, how black holes relate to quantum theory, and whether the event horizon behaves exactly as classical relativity predicts. These are not minor technical questions tucked politely into the corner of a graduate seminar. They strike at the heart of what the universe allows. If information can genuinely vanish, then one of the central assumptions of quantum mechanics is in trouble. If it cannot vanish, then something about our understanding of black holes needs revision. Either way, black holes are not just exotic objects hanging out in deep space. They are stress tests for physical law. Even before we get to those deeper problems, the approach to a black hole forces us to give up some ordinary habits of thought. We tend to imagine objects as sitting in space while time ticks forward in the same general way for everyone. Relativity already tells us that this picture is incomplete. Motion affects time. Gravity affects time. Clocks at different altitudes do not agree perfectly. Satellites must account for this. Time is not one universal stream running identically everywhere. Near a black hole, these effects become dramatic. To a distant observer, something falling toward the event horizon appears to slow down, dim and redden, as if time itself is stretching thin. To the falling traveller, however, the experience can be very different. They continue inward without noticing some cosmic pause button clicking into place. Both descriptions matter, both are real within their own frames, and black holes demand that we hold those seemingly contradictory viewpoints without dropping either one. That alone is enough to make the subject worth a long, unhurried look. Black holes do not merely present strange facts. They train the mind to loosen its grip on intuition. They remind us that the universe was not designed to be easy for primates who evolved to throw sticks, judge distances, and worry about weather. Our instincts are useful on savannas, staircases, and in supermarket queues. They are less reliable near collapsed stars, which is why science matters so much here. It gives us disciplined ways to go beyond what feels obvious. There is also the matter of scale, because black holes come in different sizes, and size changes the story. Some are formed from the collapse of massive stars and maybe a few times the mass of the Sun, or perhaps several dozen times as massive. Others, found in the centres of galaxies, are enormous beyond ordinary comprehension, containing millions or billions of solar masses. The black hole at the centre of our own galaxy is a supermassive one, and though it is distant and not about to bother our evening, it still quietly governs the motions of nearby stars. Interestingly, the larger a black hole is, the gentler some effects can be at the event horizon itself. A smaller black hole may produce violent tidal forces sooner. A supermassive one may allow you to cross the boundary without immediate drama, though the deeper trip remains an appallingly bad holiday plan. All of this sets the stage for our main question: what actually happens inside a black hole? The careful answer is that we can say some things with confidence, some things with caution, and some things only with informed speculation. According to general relativity, once you pass the event horizon, moving toward the central singularity becomes as unavoidable as moving toward tomorrow. That comparison is not just rhetorical. In a very real sense, the singularity lies in your future, not merely somewhere in front of you in space. Inside the event horizon, the roles of space and time become difficult to interpret in familiar ways. The inward direction is not just a place you could choose to avoid, it is built into the structure of what comes next. That is a deeply peculiar conclusion, and it is one of the reasons black holes are often described with a kind of reverence. Not because they are supernatural, but because they reveal how far physical reality can depart from human expectation, while still obeying mathematical law. A black hole is not chaos in the everyday sense. It is not lawlessness. If anything, it is too lawful, too exact, too willing to follow gravity to its final and most uncompromising consequences. The strangeness comes from the fact that those consequences are unlike anything in our normal experience. So as we continue, we are going to treat the subject patiently. We will not rush straight to the dramatic centre and declare victory. We will begin where nature begins, with the making of a black hole itself, because to understand what happens after the collapse, we first need to understand how gravity manages to win so completely in the first place. Somewhere in the life of a massive star, the balance shifts, pressure gives way, and matter begins a descent from which the universe will eventually build one of its darkest and most revealing objects. To understand how a black hole is born, it helps to begin with something that does not seem especially black hole-like at all. A star at first glance looks stable, calm even. From far enough away it can appear like a fixed point of light, hanging in the sky with a kind of quiet confidence, as if it has always been there and fully intends to stay. But a star is never still in any meaningful sense. It is an ongoing struggle between gravity trying to pull everything inward and pressure trying to push outward. The whole life of a star is built on that balance. It is not a peaceful object, it is a long argument that happens to glow. Gravity is always present from the beginning. A star forms when a large cloud of gas, mostly hydrogen, begins to collapse under its own weight. That cloud may have been drifting for a very long time, cold and diffuse, until something disturbs it. Perhaps a nearby explosion sends a ripple through the gas. Perhaps parts of the cloud simply become dense enough that gravity takes over. However it starts, once a region begins collapsing, the material falls inward, gathers, heats up, and becomes more compact. As that young star forms, the centre grows hotter and denser, until conditions become extreme enough for nuclear fusion to ignite. That ignition changes everything. Fusion is the process that allows small atomic nuclei to combine into larger ones, releasing tremendous amounts of energy. In an ordinary star like the Sun, hydrogen fuses into helium in the core, and the energy produced creates outward pressure. That pressure resists gravity. So long as gravity pulls inward, and pressure pushes outward in a workable truce, the star remains stable. It shines, because it is spending fuel in order to hold itself up. There is something faintly comic about this if you look at it the right way. A star is basically preventing collapse by setting itself on fire in the most controlled and sustained way nature allows. That is its daily routine for millions or billions of years. Burn in order not to fall, radiate in order not to shrink, keep the pressure high enough that gravity does not win. For smaller stars, this battle can continue for an extremely long time. They burn fuel more slowly and die more gently, but black holes are not born from gentle stars. They come from the heavyweights, the massive stars that live fast, burn hot, and consume their fuel with much less patience. The more massive a star is, the greater the gravity pressing inward, and the harder the core must work to hold the whole thing up. That means hotter temperatures, faster fusion, and a shorter life. In a strange way, the biggest stars are the least economical. They are cosmic spenders, using up their reserves at a frantic pace. As the star ages, the composition of its core changes. Hydrogen fusion builds helium. Once enough hydrogen in the core is exhausted, the balance shifts again. Gravity gains ground, the core contracts, and the temperature rises further. If the star is massive enough, that higher temperature allows new kinds of fusion to begin. Helium can fuse into heavier elements, then carbon, then oxygen, then neon, silicon and others in a sequence of ever more extreme reactions. The star becomes layered inside, almost like an onion, with different fusion processes happening in shells around the centre. This part of the story is already remarkable. A massive star is not just a glowing ball of gas, it is a kind of elemental factory, forging heavier ingredients under enormous pressure and heat. Many of the atoms we take for granted in daily life were made in stars. The calcium in bones, the oxygen we breathe, the iron in blood, these things come from stellar processes. So before a massive star becomes a black hole, it first spends its life enriching the universe. It is not simply doomed, it is productive on the way down. Still, that productive phase cannot continue forever, because fusion only works as a source of support while it releases energy. And there comes a point when the core begins producing iron. Iron is the turning point, the quiet disaster at the heart of a dying massive star. Up to that stage, fusion can help resist gravity. But iron does not cooperate. Fusing iron into heavier elements does not give the star useful energy in the same way. Instead of supporting the core, the process becomes a dead end. It is as if the star has reached the limit of what it can profitably burn. Once the core is largely iron, the clock runs very fast. This is one of the most dramatic shifts in all of astrophysics. A star may spend millions of years building toward that moment, but the final collapse of the core can happen in a tiny fraction of that time. Gravity, which has been waiting patiently the entire life of the star, finally gets its chance. The outward pressure drops, the core can no longer support the immense weight above it, and so it collapses. That word collapse may sound a bit too simple for what is really happening. We are talking about matter being crushed with extraordinary speed and violence. The core shrinks rapidly. Electrons are forced into protons, producing neutrons and a flood of tiny particles called neutrinos. The density rises to astonishing levels. The outer layers of the star, suddenly deprived of the stable support beneath them, begin to rush inward as well. For a brief moment, the whole star is no longer a stable furnace. It is a catastrophe in progress. What happens next depends largely on how much mass remains in the core. If the collapsing core is not too massive, neutron pressure can halt the collapse. That creates a neutron star, one of the densest objects in the universe short of a black hole. A neutron star is already deeply strange. A city-sized object with more mass than the sun, matter packed so tightly that a spoonful would outweigh mountains. If nature stopped there, we would still have plenty to marvel at and more than enough to lose sleep over. But if the core is heavy enough, even neutron pressure is not enough. Gravity keeps going, and this is the crucial point. A black hole is born when there is no known force left capable of halting collapse. The star has reached a stage where matter cannot support itself against its own gravity. No ordinary pressure can rescue it. No internal reaction can reverse the fall. The collapse proceeds beyond the point where even light will eventually be unable to escape. Outside the core, meanwhile, The rest of the star may explode outward in a supernova, one of the brightest and most violent events in the cosmos. A supernova is not merely a star going out. It is a star ending with an enormous release of energy, blasting material into space, creating shock waves, forging heavy elements, and in some cases briefly outshining entire galaxies. It is one of the great acts of stellar destruction and redistribution. The outer layers are hurled outward, while the center falls inward. So a black hole can be born in the middle of an explosion, hidden inside a cosmic event that from a distance looks like pure radiance. There is something almost mischievous about that. One of the darkest objects in the universe can emerge from one of the brightest events in the universe. A black hole is not born in visible darkness. It may be wrapped in fire. In some cases the story is quieter, or at least quieter by the standards of catastrophic astrophysics. Not every massive star ends with a dramatic supernova that announces itself clearly. There are scenarios in which a very massive star may collapse more directly, with much of the material falling inward rather than being blasted outward. Astronomers sometimes refer to these as failed supernovae, though from the star's perspective the failure is extremely thorough. The visible explosion may be faint or absent, while the core simply disappears behind this event horizon. Imagine watching a brilliant star and then, after its long life, instead of a spectacular farewell, it simply dims and vanishes, as if the universe lost interest in explaining itself. That too may be a route to black hole birth. There are also black holes born not from a single dying star, but through mergers. Two neutron stars may spiral together and combine. A neutron star and a black hole may merge. Two black holes may merge to form a larger black hole. In those cases, the birth is less like the first formation of such an object and more like a family business expansion, but it matters because black holes are not static members of the cosmic population. They can grow, they can feed, they can collide, they can become much larger over time. Yet the classic image remains the collapse of a massive stellar core, and that image teaches something important about black holes. They are not made from exotic material in the sense people sometimes imagine. A black hole is not composed of special dark matter from another realm. It begins with ordinary matter, the same basic ingredients found elsewhere in the universe, pushed to extraordinary conditions. Hydrogen, helium, carbon, oxygen, iron, the familiar cast of stellar material, carried by gravity into a regime where familiar structure cannot survive. The black hole is not born because nature introduces a new substance. It is born because gravity compresses known matter past every ordinary stopping point. This is where the idea of escape becomes important. To leave any object, whether a planet, a star, or an especially clingy moon, you need enough speed to overcome its gravitational pull. For Earth, that speed is high, but achievable in principle. For the Sun, it is much higher. If an object becomes compact enough, the required escape speed rises. A black hole forms when that escape condition crosses the most severe threshold of all, the point where escaping would require moving faster than light. Since nothing can do that, the boundary is set. Once enough mass is compressed into a small enough region, an event horizon forms. That is the moment the object becomes a black hole in the full physical sense. It is worth pausing there, because people often imagine black holes as sucking things in with some special extra force. But that is not how the birth works. The birth is about compression and confinement. Matter collapses, gravity intensifies, and a boundary appears beyond which outward escape is no longer possible. The black hole does not switch on like a vacuum cleaner. It becomes a region of space-time from which paths outward are cut off. Rotation can complicate the picture, and in nature it usually does. Stars spin, gas clouds spin. Collapsing objects tend to spin faster as they shrink, just as a figure skater spins faster when pulling in their arms. So a newborn black hole is often rotating, sometimes very rapidly. That spin affects the surrounding space-time. It changes the structure around the black hole and influences how nearby matter behaves. If gas falls in, it may form a rotating disk around the black hole, heating up enormously as friction and gravity work on it. That hot disk can glow fiercely. In some cases, powerful jets of material are launched from the region around the black hole, blasting outward at high speeds. So although the black hole itself does not emit light in the normal sense, the area around a newly formed one can be extremely active. And here the story becomes richer than the usual image of a dark sphere sitting quietly in space. A black hole may be hidden inside a system full of motion, heat, radiation, and violence. Gas swirls in, magnetic fields twist, X-rays pour out from surrounding material, nearby stars may be disturbed. Space around the black hole becomes a place where matter is heated, torn, accelerated, and rearranged. The darkness at the centre is real, but the neighbourhood need not be calm. There is another feature of black hole birth that deserves attention, because it reveals something slightly unsettling about the universe. From the outside, the details of the collapsing star matter much less than you might expect. The star may have had a rich internal structure, complicated layers, magnetic fields, turbulence, and perhaps a rather eventful personality if stars had that sort of thing. But once a black hole settles down, most of those details are no longer visible in the same way. To a distant observer, the black hole is described mainly by a few basic properties such as mass and spin. In that sense, black hole birth is an act of simplification through extreme collapse. The star loses much of its individuality on the way in. Whatever drama produced the object, the end result is startlingly stripped down. That simplification is scientifically useful, but also philosophically odd. Nature begins with a complex star and ends with something that can be described from the outside with astonishing economy. It is a bit like taking a grand library full of stories, compressing it beyond recognition, and being left with a locked vault labelled only by weight and rotation. The question of what happened to all the finer information, and whether it is truly lost, will become one of the deepest puzzles in black hole physics later on. But even at birth, you can already feel that puzzle taking shape. The timing of black hole formation is also subtle. To the collapsing matter itself, the plunge inward can happen in finite time. The material crosses the event horizon and continues inward according to the logic of general relativity. But to a distant observer, things can look different because of gravitational time effects. Light escaping from near the forming horizon becomes increasingly redshifted and delayed. The collapse appears to slow. Signals become weaker and more stretched out. This creates one of those classic relativity moments where two descriptions must be held together carefully. The black hole forms as a physical reality, but the outside view of material approaching the horizon becomes increasingly drawn out. There is no contradiction, only the universe insisting that perspective matters. As for the newly born black hole itself, it does not sit there as a hollow bubble or an empty tunnel. The word hole continues to do a lot of misleading work. What is really born is a trapped region, a place where geometry has become so warped that future-directed paths lead inward. The matter that collapsed helped create that region, but once the event horizon is there, the essential story is no longer about a surface or a shell. It is about space-time and what it now permits, and that is why the birth of a black hole is one of the most important transitions in astrophysics. A star begins as gas under gravity. It lives by fusion, balancing inward pull with outward pressure. It grows more complex as it ages, building heavier elements in its core. Then at the limit, when pressure can no longer keep up, the core collapses. If enough mass is concentrated and no force can halt the fall, an event horizon forms, and a black hole enters the universe. What remains outside may explode, glow, swirl, and scatter elements across space. What remains inside is cut off from ordinary escape. From there, everything changes. Because once a black hole exists, the next question is no longer how the star failed to hold itself up, but what kind of region that collapse has created. Gravity is no longer just strong. It has taken on a geometry that reshapes the meaning of distance, motion, and direction itself, which is where the story becomes less about the dying star and more about the invisible structure surrounding what it has become. Once that collapse has happened and a black hole has come into being, the next thing we have to understand is not what it looks like in the ordinary sense, but what kind of shape it gives to the space around it. That is where black holes become difficult in a very specific way, because the most important part of them is not visible. There is no surface in the everyday sense waiting politely for a flashlight. There are no walls to knock on, no rim to peer over, no giant cosmic drain cover with a warning label and a rope barrier. What matters first is the structure of gravity around the black hole, and that structure is not something you can see directly. You infer it through motion, through light, through the behaviour of matter, through the way nearby objects are forced to move. This is why the phrase invisible shape is so useful here. A black hole has mass, and mass changes the geometry of space and time. So the black hole gives shape to its surroundings, but not the way a mountain or a building does. It shapes the routes things can take. It shapes which paths are easy and which are impossible. It shapes how clocks run, how light bends, how matter falls, and eventually whether escape is still an option at all. To get there, it helps to let go of one of the oldest habits in our thinking about gravity. For a long time, gravity was understood as a force pulling objects together across empty space. That picture works very well for a great many practical purposes. It can tell you how planets orbit, how objects fall, how moons behave, how tides work, and why it is unwise to balance a bowl too close to the edge of the table if you own a cat with strong opinions. But when gravity becomes very strong, that picture starts to hide as much as it reveals. Einstein gave us a deeper one. In his view, gravity is not merely a pull, it is the effect of curved space-time. That phrase can sound more intimidating than it really needs to. Space-time simply means that space and time are not separate background stages with events happening on top of them. They're woven together into a single structure, and mass and energy change that structure. Objects then move through that changed geometry. In ordinary life, space-time is curved only mildly, so the world seems flat enough, and time seems steady enough that you can go years without giving the matter a second thought. Near a black hole, the curvature is no longer mild. It becomes so severe that the geometry itself starts doing things our instincts are not prepared for. People often use the image of a heavy ball placed on a stretched sheet, making a dip that smaller balls roll into. This analogy is useful up to a point. It helps show that mass can change the shape of the surrounding region, and that nearby objects respond to that changed shape. But it also has limitations. For one thing, the stretched sheet uses gravity to explain gravity, which is a bit like using a ladder to explain how ladders work. And more importantly, a black hole is not just a dip in space. Time is involved as well, and time does some of the most important work. Still, the central idea is sound. A black hole does not pull things inward because it is secretly grabbing at them with an invisible hand. It changes the structure of space-time so drastically that moving inward becomes the natural course. The closer you get, the more all possible paths are bent toward the black hole. At first, this is only an exaggeration of what happens around any massive object. The Earth curves space-time. The Sun curves space-time more strongly. A black hole takes that same principle and drives it into an extreme regime. Now, when we talk about the shape of extreme gravity, we should be careful about the word shape, because there are two meanings running side by side. There is the shape of the object itself, and there is the shape of the gravitational field around it. For a simple, non-rotating black hole, the object is usually treated as perfectly spherical from the outside. That is not because nature loves tidy diagrams, though it sometimes seems suspiciously fond of them. It is because when matter collapses without complicated leftover structure, the resulting black hole settles into a remarkably simple state. From outside, a non-rotating black hole is spherical. But the more interesting shape is not the surface shape. It is the geometry around it, the region of distorted space-time that spreads outward and determines how things move. If the black hole is rotating, which in nature many of them are, the situation becomes richer. Rotation twists space-time. It is not just that the black hole sits there being massive. Its spin drags the surrounding geometry around with it. This effect is called frame dragging, though the name makes it sound almost too casual, as if space-time is being pulled along slightly by a trolley, rather than twisted by an object of terrifying density. Around a rotating black hole, the geometry is no longer perfectly simple or symmetric in every direction. The space around it is stirred by spin, and this has consequences for matter, light, and the shape of the regions near the black hole. But before rotation complicates things, it is worth appreciating just how strange even the simplest case already is. Imagine moving toward an ordinary planet. Gravity grows stronger the closer you get, but the basic structure of the world remains intuitive. You can still move away if you have enough speed. Light can still leave. Signals can still travel outward. A black hole begins from the same principle but reaches a point where the geometry becomes so steep, in a sense deeper than any normal language can quite capture, that escape becomes impossible, and yet nothing announces this with a flashing sign. There is no glowing red boundary in space that says from here on out, regrettable decisions become permanent. This is one reason black holes are often hard to imagine. Their most important features are not visible surfaces but invisible limits built into geometry. If you could somehow map the influence of a black hole, you would not be drawing a solid sphere with a menacing expression. You would be drawing a region where the bending of paths becomes more and more severe. Far away, things behave almost normally. Closer in, light curves noticeably. Matter whirls faster. Time passes differently. Nearer still, escape becomes harder and harder until there comes a boundary where outward motion no longer leads outward in the way you mean it to. That boundary, which we will spend much more time with next, is called the event horizon. But even before reaching it, the invisible shape of extreme gravity is already doing its work. One of the easiest ways to notice that shape is through orbits. Matter near a black hole can form a disk, spiraling around it because the material has angular momentum. Gas in that disk rubs against other gas, heats up, glows, and gradually loses energy. So the matter spirals inward, growing hotter as it does. This is why some of the brightest regions in the universe are found around black holes. Not because the black hole itself shines, but because the geometry it creates drives surrounding matter into violent motion and heating. Light itself also reveals the shape of extreme gravity. Since light follows the structure of space-time, a black hole can bend its path. This is not a metaphor. It is a measurable physical effect. Light from stars behind a black hole can be warped, redirected and distorted. Images can be stretched or multiplied. The black hole acts as a gravitational lens, though lens is one of those charmingly tidy words for an effect that is actually rather dramatic. It means the gravity is not merely influencing solid objects or gas clouds, it is shaping the very routes that light can take through the universe. There is also a region around a black hole where light can circle the object. This is sometimes called the photon sphere. It is not a stable place in the everyday sense. A beam of light there is balanced on a knife edge. A slight disturbance sends it either outward or inward, but the existence of such a region tells you how extreme the geometry has become. Around ordinary objects, light may bend a little. Around a black hole, it can be forced into loops. Space around the black hole is no longer just a backdrop. It behaves like a place where the straightest possible paths are astonishingly far from what common sense would call straight. And then there is time. It is easy to talk about curved space and forget that time is equally part of the story. But near a black hole, the behavior of time becomes one of the clearest signs that gravity is really geometry. Clocks near a strong gravitational field run more slowly compared with clocks farther away. This is not illusion or mere appearance. It is a real physical difference in how time passes. Near the Earth, the effect is tiny but measurable. Near a black hole, it becomes enormous. If you watched a clock descending toward a black hole from a safe distance, you would see it tick more and more slowly. Light from it would become redder and weaker. Its motions would seem stretched out. To the person carrying that clock, things would feel different. Their own time would continue normally from their point of view. they would not look down at their watch and find the hands moving through syrup. That is one of the most difficult and important features of relativity. Different observers can describe the same situation in ways that do not match ordinary intuition, and both descriptions can still be valid in their own context. The invisible shape of extreme gravity is not just about where things are allowed to go, it is also about how time itself is distributed across the region. This makes the area around a black hole deeply unlike any place our brains evolved to navigate. We're used to thinking that space tells us where and time tells us when, and those are more or less separate concerns. Around a black hole, the two are tied together so tightly that the route through space and the pace of time become inseparable parts of one structure. The black hole does not simply occupy a place, it reorganizes the possibilities of place and duration nearby. One way to think about this is to imagine that every object is always moving into its future. In ordinary life, that future feels open in many spatial directions. You can step north, south, east, west, or stay in bed and negotiate with the morning for a few more minutes. Near a black hole, gravity alters the future itself in a directional way. The closer you get, the more strongly future paths lean inward. At the event horizon and inside it, this becomes decisive. But even outside, the tilt is already there in growing strength. Another clue to the invisible shape comes from tidal forces. Gravity is not only about overall attraction, it also varies from one place to another. If one side of an object is closer to a massive body than the other side, the gravitational pull on the nearer side is stronger. This difference stretches objects. Around the Earth, tidal forces raise ocean tides. Around a black hole, they can become enormous. The shape of extreme gravity is not uniform. It changes sharply with distance, and that changing strength matters. It means a person or spacecraft approaching a black hole may feel very different forces at head and feet, front and back, depending on size and distance. Interestingly, the size of the black hole changes how this plays out. A smaller black hole can have very strong tidal effects already near the horizon. A supermassive black hole can have weaker tidal effects at that same boundary, because the horizon is larger, and the gradient in gravity there can be gentler. This is one of those facts that seems rude on first encounter. It turns out the larger black hole may be less immediately aggressive at the point of no return. Not kind, certainly not safe, but less abrupt. Nature loves this sort of detail, where the simpler picture turns out to be wrong, in a way that is both irritating and fascinating. So the invisible shape of extreme gravity is not just one thing. It is a combination of curvature, time distortion, path bending, tidal stretching, and in many cases rotational twisting. It affects matter and light alike. It determines which orbits are possible, which are stable, and which lead inevitably inward. It controls how energy is released by infalling gas. It influences the appearance of the black hole to outside observers. It is the true architecture of the black hole, more than any imagined dark sphere. And this is why black holes are best understood not as holes punched into the universe, but as regions where the rules for movement have been profoundly altered by geometry. A mountain is an object you can walk around. A cave is an emptiness inside rock. A whirlpool is a flow in water. A black hole is none of these, though people borrow all of them in desperation. The better description is more severe and less visual. A black hole is a domain in space-time where curvature has become so intense that the usual distinction between possible and impossible routes begins to collapse. There is also something instructive about the fact that we cannot see this shape directly. Much of science works exactly this way. We do not see gravity itself. We see apples falling, planets orbiting, light bending, clocks disagreeing. We infer the structure from its effects. In the case of black holes, that inference has become remarkably powerful. We have observed stars whipping around invisible massive centers. We have detected radiation from accretion disks. We have imaged the shadow-like outline cast by the region around a supermassive black hole. we have measured gravitational waves from colliding black holes, tiny ripples in space-time itself, arriving after unimaginable events across the cosmos. Piece by piece, we have learned to read the invisible shape through what it does. Perhaps the most important thing to carry forward is this. Extreme gravity does not merely make things heavier or harder to escape. It reshapes the local meaning of motion. It changes what straight means. It changes what outward means. It changes how time is shared between observers. It bends light, guides matter, and prepares the way for the most famous boundary in black hole physics. Because once the geometry has become severe enough, there comes a point where all the inward-leaning possibilities become final, and the invisible shape of gravity hardens into a line the universe will not let you cross back over. And that line, strange though it is, brings us to one of the most famous ideas in all of modern physics, the event horizon. People often talk about it as though it were the black hole itself, but it is better understood as a boundary, a threshold, a limit built not from matter in the ordinary sense, but from the structure of space-time. It is the place beyond which returning to the outside universe is no longer possible, not difficult, not unlikely, not requiring a better engine or a bolder attitude. Impossible. That word impossible deserves to be handled carefully, because in everyday life we use it rather loosely. Missing a train by 20 seconds can feel impossible to recover from, though a taxi, a snack, and a revised plan may yet save the day. The event horizon is nothing like that. It is not a practical barrier. It is a fundamental one. Once something passes inward across that boundary, there is no path through space-time that leads back out to the wider universe. Every future it can have remains inside. The outside world may continue without it, but it will not rejoin that world. The first thing to say is that the event horizon is not a solid surface. This is one of the most common and understandable misunderstandings. Because we talk about crossing it, it is tempting to imagine something like an invisible shell, a dark membrane, perhaps a cosmic wall with a very strict admissions policy. But according to classical general relativity, the event horizon is not made of any known material. You do not smack into it like glass. You do not hear a thud. You do not find a sign saying last chance to turn back. If you are falling into a sufficiently large black hole, and if local tidal forces at the horizon were mild enough, you might cross it without any immediate local drama at all. That is one of the most unsettling features of the whole subject. The point of no return need not announce itself in any dramatic way to the traveller who passes through it. There may be no flash, no jolt, no physical sensation uniquely tied to the horizon itself. The significance of the boundary is global rather than local. It is about what space-time allows from that point onward, not about a special substance sitting there waiting to greet you with a clipboard. This distinction between local experience and global structure matters enormously. In normal life, boundaries are usually obvious because they correspond to physical changes. A doorway separates rooms. The shoreline separates land and sea. The edge of a cliff tends to make its views and consequences very clear. The event horizon is different. Its importance is not that it looks different right where you are. Its importance is that beyond it, the entire causal relationship between you and the outside universe has changed. Messages you send outward will never arrive. Light you emit will not escape. Any attempt to move outward still carries you further inward in the larger geometry of space-time. To appreciate how profound that is, it helps to think about escape in a more ordinary setting. On Earth, if you throw a ball upward, gravity slows it. If you throw it fast enough, it goes higher. Fast enough still, and it could in principle escape Earth altogether. The same logic applies around stars and planets. Gravity may be strong, but escape remains part of the menu if you have enough speed and energy. Around a black hole, the event horizon marks the place where that menu closes. Once you're inside, the idea of escape velocity ceases to be a useful ambition, because escaping would require something even light cannot do. And if light cannot get out, then no signal, no object, no delayed apology, and no heroic last-minute course correction can get out either. This is why the event horizon is often described as a one-way boundary. Things can cross inward, but nothing crosses back outward. Matter can fall in, radiation can fall in, entire stars can wander too close and be torn apart, their gas spiralling inward in a bright and furious display. But once that material passes the horizon, the outside universe loses direct access to it. The black hole may still reveal some basic things about what it has absorbed through its mass, charge and spin, but the detailed story of the infalling matter is no longer available in the ordinary way. There is a peculiar elegance to that. The horizon is not merely a place where things vanish from view. It's a place where cause and effect are fenced off. In a sense, it divides the universe into regions that can still influence one another and regions that cannot. That is why the word event appears in its name. Events inside the horizon cannot affect distant outside observers by sending signals outward. Whatever happens there stays there, at least according to the classical picture. From far away, however, the story looks deeply strange. If you watch an object fall toward a black hole from a safe distance, you do not see it cross the horizon in some tidy cinematic moment. Instead, because of the intense gravitational effects on time and light, the falling object appears to slow down as it approaches the boundary. Its clock appears to tick more and more slowly. The light it emits is stretched to longer wavelengths, becoming redder and dimmer. The object seems to fade, linger, and asymptotically approach the horizon without quite cleanly disappearing in finite outside time. It is as though the black hole edits the final moments into an endlessly stretched farewell. This is one of those places where relativity can feel less like science, and more like a deliberate attempt to make everyone uncomfortable. From the point of view of the falling traveller, they continue inward and cross the horizon after a finite amount of their own time. They do not hang forever in a frozen state, wondering why the universe has become uncooperative. Their watch ticks normally. Their body ages normally. Their local physics proceeds normally, at least until stronger gravitational effects deeper in begin to matter. Yet the distant observer tells a different story, one in which the traveller appears to slow and fade near the boundary. These two descriptions are not contradictory. They are consequences of how space-time behaves around the black hole. The distant observer is limited by the light signals that can still reach them, and those signals become more and more delayed and weakened as the traveller approaches the horizon. The traveller, by contrast, is not watching themselves from far away. They are simply following their own path through space-time. The event horizon sits at the intersection of these differing descriptions, a boundary that is physically meaningful even though it is not experienced in the same way by all observers. This makes the horizon unlike almost any boundary in ordinary experience. It is real, but not in the crude sense of a wall. It is significant, but not because it looks unusual to someone crossing it. It is final, but that finality is built into the geometry of the future rather than into some dramatic local sensation. In this respect, the event horizon is one of the purest examples in physics of a concept that only fully makes sense when you stop insisting that reality conform to intuition trained on everyday objects. There's another way to think about it that helps some people. Outside the horizon, if you imagine all the possible directions a flash of light could move from a given point, some directions still lead outward away from the black hole. Gravity may bend those directions and make escape harder, but outward possibilities still exist. At the horizon, those outward possibilities are pared down to an extreme limit. Inside it, all future-directed light paths lean inward. This is a profoundly geometric statement. It means the structure of space-time is tilted so completely that moving toward the centre is no longer merely likely. It is built into the shape of what comes next. That is why physicists sometimes say that inside the horizon, moving toward the singularity is as unavoidable as moving toward tomorrow. It is not simply a matter of being dragged by a force you might fight with enough determination. It is more like being carried toward the future itself. You can no more refuse that inward progression than you can decide by sheer stubbornness to stop all moments after noon from arriving. One can admire the optimism of such resistance, but the universe will not be moved by it. For a non-rotating black hole, the event horizon has a clean spherical geometry from the outside. Its size depends on the mass of the black hole. More mass means a larger horizon. This leads to an interesting point that often surprises people. The horizon is not some tiny pinprick necessarily associated with all black holes. A supermassive black hole can have an event horizon larger than the orbit of planets. It is vast. The black hole at the centre of a galaxy may have a horizon of enormous size, even though the black hole itself remains dark and difficult to picture in the usual way. And yet, for all its enormous importance, the horizon does not mark the place where gravity suddenly becomes infinite. That idea belongs more properly, if at all, to the singularity predicted deeper inside by classical relativity. At the event horizon itself, gravity may be strong, but its local effects depend on the size of the black hole. For a smaller stellar mass black hole, tidal forces near the horizon may be severe. For a supermassive black hole, they may be relatively gentle at the crossing point. This means that falling through the horizon of a very large black hole could, in principle, happen without immediate destruction. A fact that is intellectually fascinating and practically unhelpful. The horizon also matters because it defines what makes a black hole a black hole. Dense stars can be strange. Neutron stars can be astonishingly compact and powerful, but so long as light can still escape from their surfaces, they are not black holes. The event horizon is the decisive threshold. It is the point at which the object ceases to be merely dense and becomes a region causally cut off from the external universe. You might say that a black hole is less an object with a hidden inside than a territory marked by a horizon. Of course, once that territory exists, the question arises whether the horizon is truly as uneventful as classical relativity suggests. This is where modern debates enter. Some physicists have proposed that quantum effects might alter the story at or near the horizon. There have been ideas about firewalls, exotic quantum structures, and information-preserving mechanisms that would make the horizon less smooth and more dramatic than Einstein's theory alone implies. These proposals come from deep tensions between relativity and quantum mechanics, especially when one tries to understand what happens to information that falls into a black hole. The matter is still unresolved. So while the standard classical picture tells us the horizon is locally unremarkable for an infalling observer, the final word may not yet have been spoken. Even without those deeper debates, the horizon creates plenty of conceptual trouble. It invites the question of where a falling object is, especially from the point of view of a distant observer who never quite sees it cross in a straightforward way. Has it crossed? Is it frozen just outside? Is the whole notion dependent on perspective? The best answer is that the event horizon is not about what a distant observer literally watches in real time through a telescope. It is about the global causal structure of space-time. The horizon exists as a boundary of no return, even though the visual story told by outgoing light near it becomes increasingly stretched and incomplete. This difference between what is seen and what is physically true under the larger geometry is important in many areas of science, but black holes make it impossible to ignore. They remind us that vision is not a privileged route to truth. What arrives at your eyes or instruments is shaped by the paths light can take, and those paths are precisely what the black hole distorts so powerfully. The horizon is not something you locate by watching a neat crossing. It is something defined by the very fact that after a certain point, no outward light path reaches the outside universe. There is a quiet severity in that definition. It makes the event horizon less like a dramatic cliff edge and more like a legal boundary written into space-time itself. Once crossed, there is no appeal, no exception for good behaviour, no final clause covering unusual circumstances. It is the universe at its most unforgivingly clear. And still, the horizon is not merely a symbol of doom. It is also an extraordinary scientific object because it marks the place where several major ideas in physics converge. Gravity, time dilation, causality, thermodynamics, and quantum theory all gather around black hole horizons in ways that have transformed theoretical physics. Black holes are not interesting only because they are dangerous to hypothetical travellers. They are interesting because the horizon turns abstract questions into unavoidable ones. What counts as information? How does gravity relate to quantum mechanics? What is entropy in a gravitational system? Does the universe preserve all details of its history, or can horizons genuinely erase things? These are questions sharpened by the existence of event horizons. This is also why the horizon has such a strong hold on imagination. Humans are fascinated by thresholds. Shorelines, doorways, mountain passes, frontiers, all of them carry psychological weight because they separate known from unknown. The event horizon is perhaps the most absolute threshold science has identified. Beyond it lies a region that cannot report back in the normal way. That alone gives it enormous symbolic force. But the real physics is even more interesting than the symbolism, because the horizon is not just mysterious, it is precise, it is exact. It is a mathematically definable boundary where the possibilities open to matter and light are changed in a fundamental way. One detail often lost in popular discussions is that the horizon is not a one-size-fits-all experience. The approach depends on the black hole's mass and rotation, on the trajectory of the infalling object, and on what is happening nearby. A black hole with an accretion disk can surround itself with searing radiation, magnetic activity, and hot plasma. In that case, the neighbourhood outside the horizon can be far deadlier than the horizon itself. One could be fried, torn, or otherwise rendered unsuitable for further adventure well before reaching the boundary. The event horizon is the ultimate limit, but it need not be the first problem. For rotating black holes, the geometry becomes even richer because the black hole drags space-time around with it. This creates an outer region called the ergosphere, where remaining still relative to distant space becomes impossible. One can still escape from the ergosphere, unlike from beyond the horizon, but the spinning geometry allows for unusual effects involving energy extraction. The event horizon remains the true point of no return, but around rotating black holes the road to it becomes more complicated and more interesting. Nature rarely stops at one layer of strangeness when several are available. What matters most for us right now is the conceptual shift the horizon forces on us. It asks us to stop imagining gravity as something that merely pulls harder and harder until nothing gets away. That description is not entirely wrong, but it is too shallow. The deeper truth is that the event horizon marks a change in the structure of space-time itself. It is where outward-directed futures cease to connect to the outer universe. It is where causality closes in. It is where the black hole becomes not just a massive object, but a domain from which no message returns. So when we speak of the point of no return, we are not using dramatic language for effect. We are naming a literal feature of the world as described by our best theories. There exists, according to general relativity, a boundary around black holes beyond which all roads inward are one way. And once that idea settles in, the next question almost asks itself. If the event horizon is so final, so oddly uneventful to cross, and so absolute in its consequences, then what would the outside universe actually seem to do from different points of view as something approaches it, lingers near it in appearance, and slips into that region where direct contact is lost? From a safe distance, the approach to a black hole looks nothing like most people expect. Popular imagination tends to picture something dramatic and immediate, as though the moment an object nears the boundary of a black hole, it simply drops out of existence like a stone vanishing into deep water. But the view from far away is stranger, slower, and in some ways more unnerving. An outside observer watching matter fall toward a black hole would not see a clean plunge followed by instant disappearance. They would see something that appears to slow down, fade, redden, and linger. That difference between what the falling object experiences and what the outside observer sees is one of the most important consequences of general relativity. Black holes do not merely trap matter, they distort time and light in ways that make the process of falling inward look profoundly different depending on where you are watching from. And because we are the distant observers in nearly every real astronomical situation, this outside view is not just a thought experiment, it is the point of view from which actual astronomy must be done. Let us begin with something simple. Imagine that a spacecraft is falling toward a black hole. It is not yet inside, it is simply descending, broadcasting a steady signal back to a distant station. Perhaps the station receives a pulse once every second according to the clock on board the falling craft. In an ordinary setting, around a weak gravitational field, those pulses would arrive at nearly the same rhythm they were sent. There might be a small delay because light takes time to travel, but nothing deeply surprising would happen. Around a black hole, especially near the event horizon, the story changes. The first thing the outside observer notices is that the pulses begin to arrive more slowly, not because the spacecraft has decided to become less communicative, and not because its own clock is malfunctioning, but because time is passing differently in the strong gravitational field near the black hole. From the distant point of view, clocks closer to the black hole run more slowly. This is gravitational time dilation. It is not a flaw in the theory, it is one of its most central predictions. The nearer the spacecraft gets to the horizon, the more its clock appears to slow. So if the spacecraft sends a pulse every second according to its own onboard clock, the distant observer might receive them spaced farther and farther apart. 1 second, then a bit more, then more still. The rhythm stretches, the signal drifts. What looked like a regular heartbeat from the falling craft becomes more like a slowing metronome, the intervals lengthening as the craft approaches the point of no return. This alone would already make the fall look peculiar, but there is another effect layered on top of it. The light carrying those signals loses energy as it climbs out of the black hole's gravitational field. Its wavelength is stretched. To the outside observer, the light becomes redder. This is called gravitational redshift. If the spacecraft were glowing visibly, its light would gradually shift toward longer wavelengths. It would appear dimmer and redder as it fell deeper. Eventually, much of its light would slip beyond visible wavelengths altogether. The craft would not only seem to slow down, it would also seem to fade from sight. That fading matters because it means the outside observer does not watch the spacecraft hover forever in some crisp, frozen image just above the horizon. That is another popular misunderstanding. It is true that in the distant description, the infalling object appears to approach the horizon ever more slowly. But it also becomes increasingly redshifted and faint. In practical terms, it disappears from observation. The final signals become weaker, more delayed, and harder to detect until they are lost in the noise of the universe. So the object is not seen as a bright statue suspended forever at the edge. It is seen as something whose last visible traces become stretched thin and dim. There is something deeply eerie about that. The outside observer never quite receives a tidy final message saying, "Now I have crossed." Instead, the object seems to dissolve into slowness and darkness. It leaves behind a fading trail of evidence rather than a clear visual conclusion. From far away, the black hole turns the act of crossing into an ever more delayed and weakened story. Yet from the point of view of the falling traveller, none of this feels like stalling. Their own clock runs normally for them. Their heartbeat, their thoughts, their shipboard instruments all continue in ordinary local time. If they are falling into a sufficiently large black hole and are not yet being torn apart by tidal forces, they may notice nothing especially dramatic at the horizon itself. They do not freeze. They do not watch the universe speed infinitely ahead in some neat cinematic montage. They simply continue inward and cross the boundary in finite time according to their own experience. This is where black hole physics forces us to abandon the idea that there must be one single obvious answer to what happens. The outside observer sees the fall stretched and fading. The infalling observer experiences a continued descent. Both accounts are valid within general relativity. They are not competing stories where one must be wrong. They are different descriptions shaped by how space-time distributes time and light between observers in different regions. To understand what the outside observer would actually see, it helps to imagine not just one spacecraft, but a whole sequence of falling events. Suppose an astronaut drops a series of glowing beacons toward the black hole one after another, each programmed to flash steadily. As each beacon falls deeper, its flashes arrive more slowly and at redder wavelengths. The later flashes from lower down become more stretched than the earlier ones. To the distant watcher, the whole procession would seem to compress toward the horizon, in position while stretching outward in time. The lower beacons would appear to move more sluggishly, their signals more delayed and faint until the entire lower region became effectively invisible. This creates the outside impression that the black hole is surrounded by a kind of time-distorted shell where events seem to slow and dim. But again, that shell is not a material region. It is the observational consequence of extreme gravity affecting clocks and light. If instead of a spacecraft you watched a star wander too close to a black hole, the story would become more violent and more spectacular. The star could be torn apart by tidal forces before crossing the horizon. Long streams of gas would be pulled away, heated, and flung into swirling orbits. From the outside, you might see an enormous flare of radiation, as this debris forms an accretion flow around the black hole. In such a case, what you see is not a quiet dimming object, but a blazing display produced by matter still outside the horizon or approaching it. The black hole itself remains dark, but the death of the star can light up its surroundings dramatically. This is an important point because the outside observer often does not see the black hole directly. What they see is the effect of the black hole on nearby matter and light. They see hot gas spiraling inward, they see X-rays from heated plasma, they see stars orbiting an invisible center, they see distorted light paths and sudden bursts of energy when matter is disrupted. The event horizon itself does not shine. The region around it may be among the brightest places in the universe. Now consider what happens if the black hole is surrounded by a glowing disk of infalling gas. From a distant viewpoint, that disk does not appear uniform. The side rotating toward you can appear brighter because its light is boosted by motion. The side rotating away appears dimmer. Strong gravity bends light around the black hole, letting you see warped images of the far side of the disk as well. The entire scene becomes distorted by gravitational lensing. What would otherwise be a simple ring of gas becomes a twisted and amplified structure, shaped by both motion and space-time curvature. This is part of why black holes are so visually strange in scientific simulations and telescope reconstructions. The outside observer does not see a neat dark circle cut out of the universe like an ink spot on paper. They see a shadow-like region produced by the way light is trapped and bent, surrounded by bright, warped, asymmetrical emission from hot material nearby. The black hole influences not only where the light escapes, but which paths it takes before reaching us. So the view is a mixture of absence and distortion, darkness at the center, and warped brightness around it. There is also the question of what happens to the image of the falling object itself. As the spacecraft nears the black hole, lensing grows stronger. Light from it can be bent around the black hole in complicated ways. In principle, an outside observer could see multiple distorted images or light that has circled partway around the black hole before arriving. The closer the object gets to the region where light can orbit, the more bizarre the optical situation becomes. The universe near a black hole is not content with simple perspectives. It folds the view back on itself. Still, the basic observational story remains. The object appears to slow, its light reddens, its brightness fades, its signals stretch out in time, and eventually, for all practical observational purposes, it disappears. One might reasonably ask whether this means the distant observer never truly sees anything cross the horizon. In a strict sense, if one waits for light signals arriving from ever closer to the horizon, The final crossing is postponed indefinitely in the outside coordinate description. But astronomy does not operate on infinite patience. Real instruments detect finite signals. Real observations happen over finite times, so in practice the object simply vanishes from detectable view. The black hole absorbs it, the mass and spin of the system may change accordingly, and the outside universe carries on without ever witnessing a neat visual crossing. This has an almost literary quality to it, though the physics is exact. The black hole does not give the outside observer a dramatic final scene. It gives them an asymptotic fading, a signal stretched towards silence. It is less like watching a door slam shut and more like listening to a voice recede into distance till it becomes indistinguishable from the background hum of everything else. The same principles affect not only incoming objects but clocks and processes near the black hole more generally. If some physical process occurs close to the horizon, such as matter orbiting at tremendous speed, or gas heating and emitting radiation, the timing of that activity is seen differently by distant observers. Frequencies shift, timescales stretch. The black hole effectively edits the tempo of nearby events before that information reaches the wider universe. It is a cosmic timekeeper with extremely unhelpful manners. And there is another subtlety. The outside observer is not a single universal perspective. Someone farther away sees one thing, someone somewhat closer sees another. An observer hovering near the black hole but still outside the horizon will describe the falling object differently from an observer very far away. In relativity, there is no privileged audience with perfect access to how things really look in some absolute sense. Every description depends on the observer's location and motion. What makes the distant outside observer special in these discussions is that they remain safely removed from the strongest distortions and can compare events against a relatively calm external region. This becomes especially important when considering communication. Suppose the falling astronaut keeps sending messages outward. At first, the messages arrive normally enough, then more slowly, then more redshifted. Words take longer to arrive. The pitch drops if the signal is translated into sound. If the astronaut says, "I am almost there," the outside observer may receive those words long after the astronaut has already moved much closer by their own account. Near the horizon, the delay becomes extreme. The last intelligible messages are followed by stretched fragments, then perhaps nothing recoverable at all. It is not that the astronaut has stopped speaking, it is that space-time has rendered the conversation increasingly one-sided. That loss of conversational symmetry is part of what makes the horizon such a powerful boundary. Outside observers can watch the approach only through signals that are themselves being degraded by the very region they are trying to describe. The closer the action gets to the horizon, the more the black hole controls the flow of information about it. There is a temptation at this point to ask a practical question. If the outside observer never quite sees the crossing in a clean way, does the black hole ever really form from their perspective? Or does everything merely pile up at the edge forever? This is where one must distinguish between a literal visual record and the physical structure of space-time. The black hole is not defined by whether someone with a telescope gets a satisfying final frame. It is defined by the causal geometry of the region. The horizon exists as a boundary in space-time even though the outgoing light from near it is endlessly delayed and redshifted. The outside observer may not receive a sharp visual confirmation of crossing, but the black hole still functions as a black hole. In real astrophysical environments, the matter falling in is not usually a lone clean object in an otherwise empty universe. There may be disks, magnetic fields, turbulence, radiation, collisions, and ongoing streams of gas. So what astronomers actually see is often far messier and more energetic than the tidy spacecraft thought experiment suggests. But the same core principles apply. Signals from deeper regions are more redshifted. Time near the horizon is more dilated relative to distant clocks. The black hole alters both the content and the timing of what can be observed. One of the strangest emotional consequences of this is that the outside observer seems to occupy a universe where the black hole keeps secrets by slowing them down and draining their colour away. It is not simply hiding matter behind darkness, it is editing how the final approach is revealed. The closer something gets to the boundary, the more the external world is forced to watch it in stretched, fading fragments. And yet, even from the outside, black holes are not silent. Matter falling in can scream across the electromagnetic spectrum before it is lost from view. Collisions of black holes can send out gravitational waves that ripple across the cosmos. Entire stars can be shredded in visible and X-ray outbursts. The observer sees plenty, just not the thing they most want in simple terms, namely a straightforward report from inside. That tension defines the outside view. The black hole is at once observable and inaccessible, visible through consequences and invisible in its interior. The outside observer sees a region where time appears to slow, light is bent and reddened, brightness fades, and final crossings never present themselves in an ordinary way. It is a view shaped not by dramatic impact but by the gradual surrender of information. So when people imagine watching something fall into a black hole, the truth is both less theatrical and more unsettling. You do not see a clean plunge into darkness. You see the universe reluctantly let go of the object. You watch its clock slow, you watch its light redden, you watch its signals thin out and fade, and somewhere beyond what you can still receive, the object continues inward. Which means that from the outside, the black hole is not just a place where things disappear, it is a place where the last visible traces of matter are stretched into a slow farewell, while deeper inside a very different experience is already underway. If the outside universe watches the fall as a slowing and fading approach, the view from the falling object is a very different story. This is where black holes stop feeling like distant astronomical curiosities and start becoming brutally physical. Because once you ask what it would actually be like to fall toward one, the answer is no longer only about clocks and redshift and strange geometry. It is also about bodies, forces, pressure, and the fact that gravity does not pull on every part of you equally. This unequal pull is the beginning of everything that follows. In everyday life, gravity feels remarkably uniform. Your head and your feet are both pulled toward the earth, but the difference in force between them is so tiny that you never notice it. The entire planet is large enough and your body is small enough that the gravitational field does not change very much from one end of you to the other. You live your life as a mostly intact collection of parts, because Earth has the decency not to pull your ankles much harder than your shoulders. A black hole is less polite. As you fall closer, the gravitational pull on the part of you nearest the black hole becomes noticeably stronger than the pull on the part farther away. If you are falling feet first, your feet are pulled inward more strongly than your head. At the same time, the sides of your body are pulled toward the centre as well, which has the effect of squeezing you inward from the sides. So the overall experience is not simply being dragged downward, it is being stretched along the direction of the fall and compressed across the other directions. That combination of stretching and squeezing is called a tidal effect. The name comes from the same basic principle that raises tides on Earth. The moon pulls slightly more strongly on the near side of the Earth than on the far side, and the oceans respond by bulging. The same principle applies anywhere gravity changes with distance. But near a black hole, especially a smaller one, these tidal forces can become catastrophically strong. The effect is not limited to oceans. It acts on spacecraft, on stars, on bodies, on anything extended in space. This is where the famously ridiculous but scientifically useful word appears: spaghettification. It sounds like a term invented by someone who had been awake too long in a graduate office with poor lighting, and a strong need to make physics memorable. But it describes the process rather well. As tidal forces intensify, an object falling toward the black hole is stretched into a longer and thinner shape, rather like dough being pulled into noodles. It is a funny word attached to an extremely serious outcome. To understand why this happens, imagine holding a soft object by one end while pulling more strongly on the lower part than the upper part. The lower end accelerates away first, the middle tries to keep up, and the whole thing elongates. Now imagine that at the same time the object is being squeezed inward from both sides. That is closer to what the tidal field near a black hole is doing. Your body is not merely being pulled inward as a single unit. Different parts are being asked to follow different gravitational instructions, and those instructions disagree with increasing violence as you approach the source. It is worth noting that none of this requires an event horizon. Tidal forces exist outside the black hole and can become dangerous long before anything crosses the point of no return. In some situations, the environment around the black hole may destroy you well before the horizon does anything interesting. In others, particularly around very large black holes, the horizon itself may be crossed without immediate damage, and the truly severe stretching may come later, deeper inside. The black hole does not offer one universal style of death. It varies by size, by trajectory, and by what is happening nearby. This is one of the most surprising facts for people first learning about black holes. Bigger black holes are not necessarily more immediately violent at the horizon. In fact, for a supermassive black hole, the tidal forces right at the horizon can be relatively mild. That is because the horizon lies much farther from the central region, where curvature becomes truly extreme. You're still in terrible trouble, of course. No version of this is a sensible travel plan, but the form of the trouble depends on the scale of the black hole. A small stellar mass black hole can tear you apart before or as you reach the horizon. A supermassive black hole may allow you to cross the horizon without noticing anything especially sharp at that exact moment, only for the fatal stretching to build later as you continue inward. This difference matters because it reveals something important about black holes. The event horizon is not itself a place of guaranteed mechanical destruction. It is the point of no return, yes, but the local physical violence there depends on the tidal field. A horizon is a geometric boundary. Spaghettification is a physical consequence of rapidly changing gravity. The two often go together in black hole stories, but they are not the same thing. Suppose, then, that you are falling toward a black hole feet first. At first, you may simply feel weightless, especially if you and your spacecraft are in free fall together. This often confuses people because they assume strong gravity must feel like enormous weight. But weight, in the ordinary sense, comes from being supported against gravity, like standing on the ground. In free fall, you feel weightless because everything around you is falling at the same rate. Around the Earth, astronauts in orbit are in continuous free fall and feel weightless. Near a black hole, the same principle holds. Freefall does not feel like standing under crushing weight. What you feel instead, if the gravitational field changes enough across your body, is tidal stress. At first, that stress might be mild. Then it grows. Your feet accelerate inward more than your head. Internal structures in your body begin to experience strain. Bones, muscles, organs, blood vessels, all are designed for ordinary forces, not for a field that increasingly disagrees from one part of you to another. The squeezing across the sideways directions compounds the damage. It is not a simple pull, it is a deformation. A human body is not built to remain coherent under such conditions. Tissues would stretch and tear. Blood flow would be disrupted. Pressure differences would become severe. Long before any neat noodle like final form emerged, the body would lose integrity in deeply unpleasant ways. The popular image of a person smoothly elongated into a cartoon strand is, fortunately for artists and unfortunately for realism, far too tidy. Actual spaghettification would be violent, disorganizing, and rapidly fatal. The same is true of spacecraft. We tend to imagine machines as sturdier than bodies, and in many respects they are. But even a strong spacecraft has limits. Tidal forces act on every extended structure. The front and back of the vessel want to follow different trajectories. The frame is stressed. Joints strain. Materials fail. Instruments misalign. If the black hole is small enough and the approach close enough, the spacecraft can be pulled apart piece by piece. Panels shear off. Internal supports buckle. The craft becomes debris following slightly different inward paths. Stars can suffer a similar fate if they pass too near a black hole. Tidal forces can tear a star apart, stretching it into streams of gas. Some of that gas escapes. Some forms a hot swirling disk. Some plunges inward. These tidal disruption events are among the more spectacular things black holes do to the universe around them. From far away, astronomers may see a bright flare as the star is shredded and heated. The black hole itself remains dark, but the destruction of the star lights up the surrounding region. It is the cosmic version of learning about an invisible animal by hearing what it does to the furniture. There is also an important psychological point in all this. The phrase falling into a black hole tempts us to imagine a simple downward motion, as though one descends through darkness toward a central destination. But the physical reality is much more hostile to ordinary imagery. The fall is not like dropping into a well or diving into deep water. It is a journey through a region where the geometry itself is becoming more extreme, and where that geometry is translated into stress on matter. You're not merely moving through a place. The place is progressively undoing the assumptions that allow ordinary objects to stay ordinary. That undoing begins with scale. Any object of finite size becomes a problem near sufficiently strong tidal gradients because different parts of it cannot all continue, as though gravity were uniform. The object is forced to choose between remaining intact and following the geodesics, the natural freefall paths available to each part. It cannot do both. If it tries to remain intact, internal forces develop. If those internal forces are insufficient, it stretches, cracks, or tears. So spaghettification is not some theatrical extra added on by physics for dramatic flair. It follows directly from the fact that freefall paths diverge strongly over small distances near compact massive objects. You could think of it this way. In calm spacetime, neighbouring parts of an object can fall in roughly parallel agreement. Near a black hole, neighbouring parts are given increasingly incompatible futures. The lower part is told to go more urgently inward. The upper part is told to follow, but not quite as fast. The sides are told to move inward toward the central axis. The object resists this with its internal structure until it cannot. That resistance is what you experience as strain. The failure of that resistance is what produces the final deformation. There is something almost cruelly elegant about the squeezing from the sides. Many people picture the black hole simply pulling you longwise like taffy, but the compression is equally important. The tidal field narrows you laterally while lengthening you radially. It is not just stretch, it is stretch and squeeze, as though the universe had decided that one directional indignity was insufficient and added another for completeness. If you were somehow able to observe your own body from the outside during this process, which I do not recommend even hypothetically, you would see length increase and width decrease. But your own subjective experience would likely be much less clean. Sensations would depend on neural function, blood flow, damage thresholds, and timing. Death would almost certainly occur well before any prolonged awareness of extreme deformation. Black holes are many things, but they are not known for offering extended educational feedback to their victims. Now, because the size of the black hole matters so much, it is worth lingering on the contrast. Around a small black hole, tidal forces can become lethal far from or near the horizon. This means the approach itself is the main problem. The traveller is pulled apart before crossing or right as they cross the boundary. In that case, the phrase falling into the black hole really includes being physically dismantled on the way in. Around a supermassive black hole, however, the traveller could in principle pass through the event horizon with no immediate sign from local mechanics that anything special has happened. The horizon is crossed, the outside universe is forever cut off, and the body remains temporarily intact. Only later, deeper in, as the path continues inward, do the tidal gradients become overwhelming. That delayed catastrophe is perhaps more unsettling than the immediate one. It means there can be a period after the horizon where you're still alive and falling, already beyond rescue, already in a region where every future points inward, yet not yet torn apart. The physical violence that smaller black holes deliver early, larger ones postpone. The sentence has merely been passed more quietly. As you continue inward, however, the tidal field keeps growing. The stretching becomes more severe. The squeezing becomes more intense. Eventually, no material structure can cope. At that point, whether one is discussing a person, a ship, or any ordinary object, coherence is lost. Matter is redistributed along the fall. The black hole does not care what the object once was. Biology, engineering, identity, all of that belongs to scales and conditions where matter can maintain form. Deep in the tidal regime, form becomes a temporary and defeated arrangement. One might ask whether anything could be designed to survive this: a stronger material, a reinforced craft, some elaborate future technology. But the difficulty is not merely one of toughness. Tidal forces can be arbitrarily strong as you move closer to the singular region, predicted by classical general relativity. Any finite structure can be overwhelmed if the gradients become large enough. You can make something better at resisting, but not infinitely good. The black hole is patient, and space-time has excellent leverage. This is one of the reasons black holes are such good teachers of humility. Many hostile environments in the universe invite engineering confidence. Radiation can be shielded against. Vacuum can be handled. Temperature extremes can be managed with the right design. Even strong gravity can sometimes be endured with enough support or trajectory planning. But the tidal interior of a black hole is not merely one more harsh setting to engineer around. It is a progressive destruction of the idea that a finite object can continue intact as the curvature grows without bound. There is also the issue of orientation. Falling feet first is the classic image because it maximizes the intuitive sense of differential pull between feet and head. But any extended object will suffer tidal effects regardless of posture. A body sideways relative to the radial direction will be stretched along one axis and compressed along the others according to the local field. Rotation of the object complicates the damage pattern, but does not save it. Nature is flexible about the details while remaining firm on the outcome. If the black hole is rotating, the situation becomes even more complex because the spacetime is not only curved inward, but also twisted. Frame dragging can affect trajectories. Infalling matter may orbit, precess, and distort in less symmetrical ways. The basic tidal story remains, but the exact path and stresses can become richer and messier. One of the challenges in discussing black holes clearly is that the simplest case is already hard enough, while the more realistic cases refuse to remain simple out of sheer astrophysical stubbornness. From the outside, of course, all of this is hidden behind the same slowing and fading of signals we discussed earlier. The traveller does not appear to the distant universe to be abruptly stretched into some visible noodle at the horizon. Instead, their image fades, redshifts, and disappears from effective observation. The gruesome mechanics of tidal destruction belong to the infalling frame, or to nearby local descriptions, not to what the distant observer watches in a clean visual sequence. Black holes are economical in that way. They keep the worst parts to themselves. There is a strange contrast here between what relativity allows you to feel and what it allows someone else to see. The distant observer is denied a straightforward view of your fate. You, meanwhile, are denied any useful path back out. The black hole splits knowledge itself into incompatible regions. One region can infer but not witness. The other can experience but not report. And then there is the central question hiding inside all of this. If stretching and squeezing grow stronger without limit, what are they growing toward? What is the destination of this destruction? In classical general relativity, the answer is the singularity, a place where density and curvature are driven beyond the theory's ability to remain sensible. The tidal forces are not random punishment. They are symptoms of a geometry becoming ever more extreme as inward motion continues. That means spaghettification is not the end of the story. It is the mechanical prelude to a deeper conceptual problem. The body is torn apart, yes. The spacecraft is dismantled, yes. Matter is stretched, compressed, and driven inward. But physics then faces a harder question than what happens to a person. It must ask what happens to matter, structure, and space-time itself as the singular region is approached. Because once ordinary objects have been undone by gravity, what remains is not just destruction. It is a confrontation with the point where our current theory stops giving trustworthy answers, which is where the fall becomes less about what happens to the traveller and more about what time and space themselves are doing in the interior. That is where the subject becomes even stranger. Because once the stretching and squeezing are no longer the main story, we arrive at the part of black hole physics that unsettles even people who are perfectly comfortable with stars exploding and matter being crushed to absurd densities. Inside a black hole, according to classical general relativity, time and space do not continue behaving in the familiar way. The trouble is not only that gravity is strong. The trouble is that the usual layout of reality, the quiet background arrangement that lets us say where something is and when something happens, begins to change its character. Outside the black hole, however distorted things may already be, there is still a meaningful sense in which you can imagine moving inward or outward in space. Time continues to be the thing that carries events from one moment to the next, and space remains the arena in which different directions are available. That distinction becomes harder to maintain once the event horizon has been crossed. Inside, the inward direction is no longer merely a direction through space that you might choose to take or avoid. It becomes part of your future in a way that is much closer to how tomorrow is part of your future outside the black hole. This is one of the most important ideas to understand, and also one of the most difficult to picture correctly. People often say that inside a black hole, space and time switch places. That phrase is useful as a first warning, but it can also be misleading if taken too literally. It does not mean that clocks turn into hallways or that east becomes yesterday. What it means is that the role played by the inward direction changes so much that moving toward the centre becomes unavoidable in the same structural sense that moving toward later times is unavoidable in ordinary life. In everyday experience, you can choose your direction through space. You can go left, right, forward, backward, or stay exactly where you are and argue with your own schedule. Time is different. You do not choose whether to move from one second to the next. That happens whether you approve of it or not. Outside a black hole, falling inward is still something that, in principle, can be avoided if you have the right trajectory or sufficient speed and distance. Inside the event horizon, it is no longer that kind of thing. The inward direction becomes built into what comes next. You do not head toward the singularity because you have made a poor navigation decision. You head toward it because it lies in your future. That sentence is not just a dramatic way of speaking. It reflects the geometry described by general relativity. Light itself gives us the clearest clue. Outside the horizon, if you imagine all the possible directions in which a flash of light could move, some of those directions still lead outward. Near the black hole they may be bent, delayed, and made difficult, but outward remains part of the available structure. At the event horizon, the outward paths are reduced to an extreme limit. Inside it, all future-directed light paths point inward. Since nothing travels faster than light, any object moving through space-time is even more restricted. If light cannot aim its future outside, neither can you. This is why turning around inside the horizon is not a meaningful escape plan. It is tempting to think that perhaps one could fire engines, reverse course, or simply be more determined than the average falling object. But that way of thinking assumes that the centre of the black hole is merely a place in front of you, like a mountain you could walk away from if only your legs were strong enough. In the classical description, it is not like that. The singularity is not merely a head in space, it is a head in time, and just as you cannot use effort or technology to stop the next minute from existing, you cannot use effort or technology to stop the inward progression once you are inside the horizon. This is an uncomfortable idea because it breaks one of the deepest habits of ordinary thought. We are used to space being the realm of options and time being the realm of inevitability. Inside a black hole, One direction in space acquires the inevitability of time. That does not mean the whole distinction disappears in every simple sense. You can still move in different ways locally, you can rotate, you can emit light in different directions, you can flail if you feel committed to that strategy. But none of those local actions alter the larger fact that every possible future continues deeper inward. A useful analogy, though an imperfect one, is a river heading toward a waterfall. Outside the horizon, you're still on land or in slow water, and can choose routes with enough skill. At the horizon, you cross into a current that all future movement must follow. Once you're truly in it, swimming upstream is not just difficult. The structure of the flow no longer allows the kind of upstream return you are imagining. Even that analogy is gentler than the real physics, because a river is a force in space, while the black hole interior is a feature of space-time itself. Still, it gives a rough sense of why the interior is not simply a darker version of the exterior. Another way to put it is this. Outside the black hole, the phrase later and the phrase deeper inward describe different things. Later refers to time. Deeper inward refers to position. Inside the horizon, those begin to align in a severe way. Going later means going inward. The center of the black hole is not somewhere you might or might not reach depending on your preferences. It is where your world line is headed. In relativity, a world line is the path an object takes through space-time. For anything inside the horizon, that path ends at the singularity according to classical theory. This has a very strange consequence for the meaning of stillness. In ordinary life, staying still in space is perfectly reasonable. You sit in a chair, remain in one place, and time carries you onward. Inside the horizon, staying still in the relevant radial sense is no more possible than staying still in time is outside. You cannot hover at a fixed inward position the way you might hover outside with powerful engines. The geometry no longer grants that option. The singularity is as unavoidable as the next moment. That is why physicists sometimes say that the singularity is not a place you can avoid once inside, but an event in your future. And this is not the sort of future you can reschedule by pretending not to check your calendar. It is woven into the causal structure of the interior. Every light cone, every locally allowed future direction tips inward. The black hole has altered not just the strength of gravity, but the arrangement of possibility. Now, the phrase light cone is worth handling briefly because it helps make the picture more concrete. At every event in space-time, you can think of the possible directions that light can move as defining the limits of what counts as the future. Massive objects must move within those limits. In flat, ordinary space-time, those futures are arranged in a way that lets you imagine progressing through time while retaining freedom in space. Near a black hole, the cones tilt inward. At the horizon, they tilt so far that outward escape becomes impossible. Inside, they continue to point toward the singularity. This is the geometrical heart of the matter. None of this means that an infalling person experiences time backwards, or loses all sense of sequence. Quite the opposite. From their own local point of view, time still feels like time. Their watch ticks forward. Thoughts follow one another in the usual order. Causes still precede effects locally. If they dropped an object beside them, it would behave in a way consistent with the local physics around them. What changes is not that their personal time becomes nonsense, but that the global meaning of inward and onward becomes fused in a way that has no everyday analogue. This is one reason black holes are so hard to imagine honestly. People either picture them as giant vacuum cleaners, which is much too crude, or as magical portals where everything instantly becomes surreal in a cinematic way, which is too theatrical. The actual story is more disciplined and more disturbing. The laws of relativity continue to operate. Local physics continues to make sense. But the overall arrangement of space and time becomes so altered that escape and avoidance cease to be available categories. If you try to ask how much time an infalling observer has left after crossing the horizon, the answer depends on the mass of the black hole and on the observer's path. For a non-rotating black hole, once inside, the proper time before reaching the singularity is finite. That means the infalling traveller does not spend eternity wandering a mysterious interior. In the classical picture, the journey ends after a limited amount of personal time. In a small black hole, that interval may be extremely short and tidal forces may have already done their work anyway. In a supermassive black hole, the crossing can be followed by a longer inward descent before the final region is reached. Longer, in this context, is very much a relative kindness. There is another aspect of the interior that deserves emphasis. Outside the black hole, you can meaningfully talk about orbits. Matter can circle around. Light can loop under special conditions. Objects can remain at stable distances if the circumstances are right. Inside the event horizon, stable outward-facing arrangements are gone. The geometry no longer supports the kind of stationary or orbiting future that would keep you from the centre indefinitely. This is another reflection of the same deeper fact. The singularity is not just sitting there in space as one optional destination among many. It has become the unavoidable endpoint of every time-like future. This is also why the interior of a black hole should not be imagined as a hidden room. A room suggests volume that can be occupied in a relatively normal way. It suggests that if one could only get inside, one might look around, take measurements, and perhaps complain about the lighting. The black hole interior is not like that. It is not a chamber behind a curtain. It is a region of space-time with a one-way causal structure, a region where inward progression is woven into the future itself. Now that is the classical picture, and it is important to keep saying classical, because this is exactly the kind of region where we expect our current theories to become incomplete. General relativity predicts the structure beautifully up to a point, but it also predicts a singularity. And singularities usually indicate not that nature literally contains tidy infinities waiting at the end of the road, but that the theory has been pushed beyond its domain of reliability. So when we say time and space behave this way inside a black hole, we mean that this is what the best classical theory says. It may be revised by a future theory of quantum gravity. But until that theory is fully in hand, this is the clearest map we have. That future incompleteness becomes especially important when people ask what the singularity really is. In the simplest classical description, it is the place where curvature becomes unbounded and the known equations cease to produce physically sensible outcomes. That sounds dramatic because it is dramatic. It means the interior evolution described by relativity leads to a boundary of understanding. Time and space are not only rearranged on the way in, they're driven toward a region where our current language about them becomes unreliable. So the black hole interior is not just a place where time and space act oddly. It is a place where the very framework we use to describe time and space reaches its limit. Rotating black holes make this even more complicated. A rotating black hole does not have exactly the same simple interior structure as a non-rotating one. The geometry is richer, and the mathematics allows features such as inner horizons and more elaborate causal regions in the idealized exact solutions. Popular accounts sometimes become very excited at this point and start hinting at tunnels, other universes, and all sorts of speculative passages. It is wise to be careful. These exotic possibilities arise in highly idealized mathematical models, and most physicists do not take them as reliable guides to what real rotating black holes provide. Real black holes are messy, perturbed, and embedded in physical environments. The more exotic interior structures and exact solutions are likely unstable or altered by realistic effects. So while the mathematics of rotating black holes is fascinating, it is not a good idea to treat them as convenient shortcuts through the cosmos. The universe has not handed out a public transport system just because some equations became adventurous. Even in the simpler non-rotating case, the shift in the roles of time and space can be hard to grasp, because language keeps nudging us back toward everyday imagery. We ask what is in there, how far away is the centre, can you stop, can you wait, can you aim elsewhere? These are sensible questions from outside, but inside the horizon their meaning changes, distance to the singularity is not just a matter of spatial separation, it is intertwined with the finite amount of future proper time remaining. The centre is not just there, it is coming. That phrase may sound ominous, but it is the closest plain English summary of the classical picture. Inside the horizon, you do not travel toward the singularity in the same loose way you travel toward a city or a coastline. You proceed toward it in the same deep, structural sense that all observers proceed toward later times. The future narrows into it. At the same time, your local surroundings do not immediately become incomprehensible. This is another important balance to keep. The grand structure is bizarre, but local physics remains orderly. If you carried a small laboratory with you, many experiments would still behave as expected over short times and short distances. Falling particles fall. Light moves at the same local speed. Clocks tick. Matter responds to forces. Relativity does not dissolve into fantasy inside a black hole. It remains physics. What changes is the shape of the stage on which local physics unfolds. And because the stage has changed, information becomes an even deeper problem. If every future inside leads inward, and if signals cannot return past the horizon, then what happens to the details of everything that falls in? What becomes of the information carried by matter, radiation, fields, and structure? Classical black holes seem to hide those details behind the horizon and then drive them toward the singularity. But quantum theory does not easily tolerate the idea that information is simply erased from the universe. That tension is one of the biggest reasons black holes sit at the centre of modern theoretical physics. So the deeper we go into the interior, the harder it becomes to separate questions about geometry from questions about information. Time and space inside the black hole are already behaving in a way that rewrites our ordinary categories. The next step is to ask what happens not just to the traveller or the clock, but to the actual content of what fell in. Because if the black hole interior rearranges the future so completely, then the fate of information itself becomes impossible to ignore, and that is where the story turns from strange geometry to one of the sharpest puzzles in all of physics. And this is where the question becomes even more unsettling, because once we stop asking what happens to a falling object mechanically, and start asking what happens to the information it carries, black holes cease to be merely violent places in space. They become a direct challenge to the foundations of physics. A body can be stretched, a spacecraft can be torn apart, a star can be shredded into streams of gas. Those outcomes, brutal though they are, still sound like physics as usual. Matter is rearranged, energy changes form, structures are destroyed, nature is harsh, but understandable. The information paradox enters when we ask whether the universe has truly lost track of what fell in, or whether those details survive in some hidden, scrambled, or transformed way. To see why this matters, it helps to begin with the ordinary meaning of information in physics, because it is not quite the same as the casual everyday meaning. In ordinary conversation, information sounds like facts, messages, secrets, or useful details, such as where you left your keys or whether a friend actually meant to reply 3 days ago. In physics, information refers more broadly to the full set of details that describe the state of a system. If you know the exact positions, motions, energies, and internal arrangements of everything in a system, then in principle you know it's physical information. In practice, no one ever knows all of that because the universe does not hand out such records freely. But at the level of fundamental law, many parts of physics assume that information is not simply destroyed. It may be scrambled, dispersed, hidden in correlations, or effectively impossible to reconstruct, but not erased from reality altogether. That distinction between scrambled and destroyed is essential. If you burn a book, the words are no longer readable, and for all practical purposes the book is gone. But according to the usual principles of physics, the information about what happened has not simply vanished into nothing. It has been spread into smoke, heat, ash, radiation, molecular motion, and the altered surroundings. Good luck putting it back together, of course, That would be a project for someone with infinite patience, infinite precision, and perhaps a suspicious disregard for healthy hobbies. But the key point is that destruction of usefulness is not the same as destruction of information. Black holes seem, at first glance, to ignore that distinction. Throw in a book, a chair, a star, a violin, a sandwich, a planet, or a deeply regrettable storage locker full of old tax paperwork, and from the outside the black hole appears to settle into a state described mainly by a few simple quantities such as mass and spin. The details of what fell in no longer seem to matter. The black hole does not reveal whether it consumed a library or a lunch. It simply becomes slightly heavier, perhaps slightly more angular in its motion, and otherwise remains astonishingly indifferent to the identity of its meals. This apparent indifference is already strange enough. It suggests that black holes erase complexity from view. A complicated star collapses and produces a black hole that looks simple from the outside. A beautifully structured object falls in and vanishes behind the horizon, leaving little trace of its individuality. Classical general relativity seems content with this. It tells us that the event horizon hides the interior from the outside universe, and that whatever happens deeper in is simply not available in the ordinary way to distant observers. For a while, that felt like a severe but manageable situation. Perhaps the information was still inside, safely hidden behind the horizon, no longer accessible but not necessarily gone. If the black hole just sat there forever, one might imagine that the lost details were at least stored in some inaccessible form. Hidden is not the same as destroyed. Locked in a vault is frustrating, but it is not annihilation. The real trouble began when quantum theory entered the room and, in its usual fashion, made everything more precise and more uncomfortable. In the 1970s, Stephen Hawking showed that black holes are not completely black when quantum effects are taken into account. They emit radiation. This radiation, now called Hawking radiation, arises from the interplay between quantum fields and the curved spacetime near the horizon. The black hole can slowly lose mass by emitting this radiation, and if nothing else falls in, it can in principle evaporate over immense stretches of time. That discovery transformed black holes from one-way traps into objects with thermodynamic lives. They have temperature, they have entropy, they radiate, they can shrink. And that is where the information paradox sharpens into a genuine crisis. If a black hole forms from ordinary matter, swallows detailed information, and then eventually evaporates into Hawking radiation that appears to be essentially featureless thermal emission, what happened to the information about everything that fell in? This is the paradox. Classical relativity suggests the information disappears behind the horizon and heads toward the singularity. Hawking radiation, in its original treatment, looks thermal, which means it does not seem to carry the detailed structure of what fell in. If the black hole evaporates completely, then the information appears to be gone from the universe altogether. Not scrambled, not hidden in hard-to-decode form. Gone. And that is deeply offensive to quantum mechanics, which strongly resist the idea that information can be fundamentally destroyed. It is one thing for nature to be difficult. It is another for nature to be inconsistent with itself. Black holes threaten exactly that. General relativity says one thing about horizons and interiors. Quantum theory says another thing about how physical evolution ought to preserve information. Together they produce a contradiction sharp enough that physicists have spent decades worrying at it like a terrier with a locked briefcase. To appreciate why thermal radiation is a problem, imagine you have two completely different objects, say a dictionary and a turtle, and both are thrown into black holes of the same initial mass under otherwise controlled conditions. If the resulting Hawking radiation depends only on the black hole's gross properties and not on the detailed identity of what fell in, then after full evaporation the final radiation would look essentially the same in both cases. That would mean the universe had forgotten whether a dictionary or a turtle was consumed. One does not need to be emotionally invested in either example to see that this is not how quantum theory likes to operate. The phrase black holes have no hair became a famous shorthand for the outside simplicity of black holes. It means that once a black hole settles down, it does not exhibit a rich visible variety of distinguishing features from the outside. No hair in this context means no extra visible details. But the information paradox asks whether that baldness is only skin deep or whether the black hole is truly deleting detail from the world. The answer matters enormously. If information can genuinely vanish, then quantum mechanics may need radical revision. If information cannot vanish, then our picture of black holes, horizons, or Hawking radiation must be incomplete. Many responses have been proposed over the years, and none became accepted quickly because each option comes with difficulties. One possibility was simply that information really is lost. Hawking himself initially defended that view for a time, but this move is expensive. It would mean abandoning one of the core structural assumptions of quantum theory, the idea that physical evolution preserves information in a strict sense. That is not impossible, but it is a dramatic concession, and physicists are not usually eager to throw out a central principle unless forced to do so by overwhelming evidence. Another possibility is that the information somehow remains trapped forever inside a leftover remnant after evaporation, a tiny object containing all the swallowed detail. That sounds convenient, but it creates its own headaches. Such remnants would need extraordinary properties to store vast amounts of information in tiny form, and theories that allow them can lead to troubling infinities and other instabilities. Nature rarely rewards convenience without adding a bill later. A third and ultimately more influential possibility is that the Hawking radiation is not truly featureless after all. Perhaps the information does come out, but in an extremely scrambled and subtle way, encoded in correlations within the radiation. In that case, the black hole would not destroy information. It would act more like a cosmic shredder of incomparable efficiency, taking neat input and returning a hideously disordered output that nonetheless still contains the original content in principle. Not readable, not practical, not recoverable by any method a sane person would attempt, but not fundamentally lost. This general direction has become the dominant hope in modern theoretical physics. Information is believed by many to survive, not by being preserved in some ordinary archive inside the black hole, but by being encoded in the full quantum state of the emitted radiation and the black hole together. The challenge is to explain exactly how that happens without violating everything else we think we know about horizons, locality, and quantum fields. And this is where the subject becomes wonderfully technical and mildly infuriating, because the black hole seems to force us into uncomfortable trade-offs. If information gets out, then perhaps the horizon is not as smooth and uneventful as classical relativity suggests. If the horizon remains perfectly ordinary for infalling observers, then perhaps some other principle about locality or separability has to bend. If quantum mechanics must stay intact, then space-time near the horizon may be doing something much subtler than our first classical picture implies. One especially famous flashpoint in this debate was the firewall argument. Very roughly, the idea was that preserving information in the outgoing Hawking radiation might require the horizon to be replaced, in effect, by something violent enough to break the smooth passage predicted by general relativity. In that picture, an infalling observer would not cross the horizon peacefully. They would encounter a wall of intense quantum activity, a kind of catastrophic boundary. The proposal was shocking because it attacked a principle many physicists had hoped to preserve, namely that crossing the horizon of a large black hole should feel locally ordinary if tidal forces there are mild. Firewalls were not embraced as a final answer, so much as feared as a possible sign that cherished assumptions cannot all survive together. The universe may be forcing us to sacrifice some combination of smooth horizons, ordinary locality, and simple quantum entanglement patterns. It is one of those moments in theoretical physics where several ideas everyone likes seem to fit together badly, and no one gets to leave the room with all their preferences intact. There have been other profound ideas as well. Some approaches suggest that the information is encoded on or near the horizon itself, in a way hinted at by black hole entropy. This line of thought helped inspire the holographic principle, the extraordinary proposal that the information content of a region of space may be describable by degrees of freedom associated with its boundary. In the black hole context, this means the horizon may be much more than a passive line of no return. It may play an active role in how information is stored and eventually released. That idea sounds almost impossible when first heard, and then somehow becomes even stranger when examined more closely. The holographic principle suggests that the deep interior story may in some sense be encoded on a lower dimensional boundary description. It is one of the most radical and productive ideas to emerge from attempts to reconcile gravity and quantum mechanics. In certain theoretical settings, especially through work involving anti-de Sitter space and quantum field theories on boundaries, physicists have found powerful evidence that information is indeed preserved, and that black hole evaporation need not violate quantum mechanics after all. Still, one should be careful not to oversell certainty. The broad belief that information survives is stronger now than it once was, but the exact mechanism in realistic black holes remains an area of deep ongoing research. There is no neat little card in the back of the textbook saying mystery solved, and everyone can sleep soundly. Black holes continue to expose the places where our understanding of quantum gravity is incomplete. The fate of everything that falls in is therefore not just a dramatic storytelling question. It is a test of whether the universe is ultimately coherent. If information survives, then black holes are not simple erasers. They are transformative devices, hiding and scrambling details in ways that may only become clear through a more complete theory of spacetime and quantum mechanics. If information does not survive, then one of the most successful frameworks in physics is missing something basic. Either way, black holes are not peripheral curiosities. They are pressure points in the structure of physical law. There is also something deeply human in why this problem captures us. We are creatures attached to continuity. We want actions to have consequences, causes to connect to effects, histories to remain part of reality even when inaccessible. The thought that the universe might simply delete detail at an event horizon feels like a violation of narrative itself. Not because the universe owes us storytelling consistency, but because so much of physics has taught us that beneath apparent disorder, there is still preservation. Black holes threaten to turn preservation into oblivion. Yet perhaps that language is a little too dramatic because black holes may be doing something more subtle than either perfect storage or perfect destruction. Increasingly, the emerging picture is one of profound scrambling. A black hole may take incoming information and mix it into itself with extraordinary speed, then release it very slowly in radiation that looks nearly thermal but contains delicate correlations. Recovering the original information from such radiation might be so difficult as to be functionally impossible. But functionally impossible is not the same as fundamentally absent. This distinction, frustrating though it is, may be the key to preserving both gravity and quantum theory without demanding miracles from either. In recent years, there have been important conceptual developments involving quantum entanglement, space-time geometry, and even ideas suggesting that wormhole-like connections and entanglement may be related at a deep level. Some calculations in simplified models of black holes have reproduced the expected behavior for information, preserving evaporation in ways that were once thought out of reach. These results have made many physicists more optimistic that the paradox is tractable, even if the final story remains unfinished. The black hole, rather than being a place where law breaks down irreparably, may be a place where hidden unity between gravity and quantum theory becomes visible. That would be a satisfying outcome, though the universe is not required to satisfy us. It is entirely possible that the final answer will remain unsettling. Black holes may preserve information in a way that forces us to give up cherished assumptions about space, time, or locality. They may teach us that what we call the interior and exterior are not as independent as they seem. They may reveal that space-time itself is not fundamental, but emergent from deeper quantum relationships. In that case, the fate of everything that falls in would not be a story about loss, but about the inadequacy of the categories we started with. What makes the information paradox so powerful is that it turns a seemingly remote astrophysical object into a philosophical and mathematical necessity. You do not have to fall into a black hole for it to matter. The mere existence of black holes in a universe governed by both gravity and quantum mechanics forces the issue. Either information survives, or something central in physics gives way. There is no polite middle ground where everyone keeps their favourite assumptions and goes home early. So when we ask what becomes of everything that falls in, the honest answer is that the old classical picture of permanent concealment behind the horizon is no longer enough. The modern view points toward preservation through scrambling, encoding and subtle quantum structure, though the details are still being worked out. The black hole does not seem content to be a simple grave. It behaves more like a cryptographic nightmare, swallowing clear histories and returning them, if it returns them at all, in a form so scrambled that the universe itself appears to be speaking in riddles. And that is perhaps the strangest turn in the whole story. The closer we look, the less the black hole resembles a place where physics ends, and the more it resembles a place where deeper physics begins to demand attention. The information paradox is not merely about what vanishes, it is about what must remain true if the universe is to make sense at all. Which means the next step is unavoidable, because once a black hole has forced us to confront the fate of information, we arrive at the most severe prediction classical relativity makes about its interior, the place toward which every future inside points, and where our current equations themselves begin to fail. That is the point where black holes stop being merely dangerous objects and become something even more difficult for physics to face honestly. Up to now, however strange the journey has become, there has still been a sense that our theories are doing their job. Gravity curves space-time. Time slows near the horizon. Tidal forces stretch and squeeze falling matter. Information appears to be hidden in ways that force us into deep arguments about quantum mechanics. All of that is strange, but it's still intelligible within known frameworks. The singularity is different. The singularity is where the theory that brought us this far begins to stop behaving like a trustworthy guide. When people first hear the word singularity, they often imagine a tiny glowing point at the centre of the black hole, like a bead of matter compressed into a perfectly small ball. That image is understandable, but it is too concrete and, in an important sense, too optimistic. A singularity in general relativity is not best thought of as a normal object sitting inside the black hole waiting to be photographed, if only one had stronger cameras and a truly alarming disregard for personal safety. It is a sign that the mathematical description itself has reached a place where it can no longer continue in a physically sensible way. That distinction matters. Physics uses mathematics to describe the world, and sometimes the mathematics tells us something clear and testable. Sometimes, however, the mathematics runs into infinities, undefined behaviour, or breakdowns in the structure of the theory, or breakdowns in the when that happens. It does not automatically mean nature literally contains an infinite quantity in the crude everyday sense. It often means the theory has been pushed beyond the range where it can be trusted. The singularity inside a black hole is usually taken in that spirit. It is not merely a bizarre thing predicted by physics. It is a warning flare sent up by physics, saying that our current description has reached its limit. In classical general relativity, once you pass inside the event horizon and continue inward, the curvature of space-time keeps increasing. The densities involved become more extreme, the tidal forces grow without bound. Every future-directed path leads toward the central region. According to the theory, this process does not level off into some stable hidden core. It does not end in a neat compact starlet, a hard centre, or a dense nugget of matter that simply sits there. It continues until the equations tell us that curvature becomes infinite, and the known structure of space-time ceases to extend in the usual way. That terminal feature is what we call the singularity. One of the more careful ways to describe a singularity is to say that space-time is geodesically incomplete there. That phrase sounds technical, but the idea behind it is manageable. In relativity, free-falling objects follow natural paths through space-time. If those paths can be continued smoothly forever, the space-time is complete in that sense. If instead some paths just stop after a finite amount of time, not because the object hit a wall made of ordinary matter, but because the space-time itself no longer extends in the way the theory requires, then something has gone badly wrong. The singularity is not just a very dense place. It is a place where the normal continuation of the geometry fails. That is one reason the singularity feels more disturbing than any other part of the black hole story. An event horizon is strange, but it is still part of a coherent geometry. Time dilation is strange, but it is a lawful effect. Spaghettification is violent, but it is understandable as a result of tidal gradients. The singularity is not merely another severe condition waiting deeper inside. It is where the theory points and then falters. If that sounds like a loophole or a mathematical technicality, it is not. The prediction that singularities arise under conditions like gravitational collapse is one of the major outcomes of 20th century relativity. Roger Penrose and Stephen Hawking, among others, developed powerful results showing that under quite general conditions, collapse and strong gravity lead to singular behavior in space-time. These are the singularity theorems. They did not depend on highly delicate special cases. They showed that singularities are not just artifacts of perfect symmetry or oversimplified textbook models. They arise robustly when gravity wins strongly enough. That was a profound moment in physics, because it meant the problem could not be brushed aside as a curiosity of idealized equations. If general relativity is taken seriously and matter behaves in physically reasonable ways, then gravitational collapse seems to produce regions where the theory predicts its own breakdown. In other words, the better general relativity works, the more confidently it tells us that it eventually stops being enough. There is something almost paradoxical about that. A successful theory usually earns trust by explaining more and more. General relativity explains planets, stars, light bending, time dilation, expanding space, gravitational waves, and the gross structure of black holes with astonishing accuracy. But one of the things it explains most strongly is that there are situations where it cannot be the full story. It is like a map that is so well drawn, it clearly marks the point where the paper ends. What would happen to a falling object approaching the singularity in the classical picture? The answer is not pleasant, although at that stage the details of what happens to a recognizable object become almost secondary. Long before reaching the singular region, tidal forces would have become overwhelming. Any ordinary structure would already have been torn apart. Matter would be stretched, compressed, and driven inward. Eventually, according to the theory, every part of that matter is carried toward a regime where curvature becomes arbitrarily large. This is not a normal environment where one could speak casually of surviving to make observations. The singularity is not a place for explorers. It is the end point of the classical interior. In the simplest non-rotating black hole, the singularity is often represented as a space-like feature rather than a point in the everyday sense. That means it lies in the future of anything inside the horizon. This connects back to what we discussed earlier. The singularity is not just somewhere at the centre that one might circle around or choose to avoid. It is the unavoidable future boundary of the interior space-time. Every future-directed path ends there. That is another reason why describing it as a point can be misleading. The word point makes it sound like a location in ordinary space. In the classical geometry, it behaves more like the end of time for the infalling observer. For rotating black holes, the exact mathematical structure becomes more complicated. The idealized solutions allow ring-like singularities and other elaborate features that have fueled many speculative stories in science fiction and popular accounts. Those stories often leap quickly from strange mathematics to wormholes, alternate universes, and convenient portals to anywhere that the plot requires. Caution is wise here. The exact rotating solutions are highly idealized, and the exotic internal structures they contain are widely suspected to be unstable under realistic conditions. Real black holes form in messy astrophysical environments, interact with surrounding matter, and are unlikely to maintain the delicately perfect features that make the more adventurous mathematical scenarios possible. So while the interior mathematics of rotating black holes is rich and fascinating, it should not be treated as a reliable promise of cosmic shortcuts. The deeper issue remains the same in any case. The singularity signals that our best classical description has hit a wall. And when a major theory hits a wall, physicists do not usually conclude that the universe has become impossible. They conclude that some deeper theory is needed. That is exactly what most people think is happening here. General relativity is a classical theory. It does not include the full quantum structure of nature. Black holes, especially in their deepest interiors, are places where gravity becomes extreme on scales where quantum effects can no longer be ignored. So the natural expectation is that a correct theory of quantum gravity would replace the classical singularity with something more physically meaningful. The frustrating part is that we do not yet possess a complete, universally accepted theory of quantum gravity. We have candidate approaches, we have important insights, we have powerful frameworks in certain regimes, but we do not have the final, settled account that tells us exactly what replaces the singularity in a realistic black hole. This leaves the singularity in an odd position. It is not believed to be the final truth in a naive sense, yet it remains the place where the current theory most clearly gives up. The gap invites a number of possibilities. Perhaps the singularity is smoothed out by quantum effects so that curvature becomes enormous but finite. Perhaps matter reaches a new state where space-time itself is fundamentally discrete or quantized in a way that prevents the classical infinities from appearing. Perhaps the interior undergoes a bounce of some kind under conditions very different from the classical picture. Perhaps the notion of a smooth interior space-time ceases to be fundamental, and the very language of inside and center must be replaced by something more abstract and quantum. Different approaches to quantum gravity hint at different resolutions, but none has yet become the final answer everyone agrees on. One possibility people sometimes imagine is that the singularity behaves like a crushing endpoint, where all matter is compressed into literal infinity. But infinity in physics is usually a red flag, not a destination one should reify too quickly. When an equation predicts an infinite density or curvature, it often means the variables in the theory are no longer appropriate to the regime in question. Classical fluid equations fail at atomic scales. Classical electrodynamics runs into trouble at short distances. Classical gravity likely fails in the deepest black hole interior. It is not that nature loves infinities as physical objects, it is that our approximations run out of road. This is why many physicists speak of the singularity as where physics begins to break, not where reality itself ceases. Reality keeps doing whatever reality does. The breakdown is in our description. That may sound modest, but it is actually a very important statement of scientific discipline. We should not pretend to know more than the theory can honestly support. The black hole singularity is one of those places where honesty requires restraint. Even so, the singularity is not meaningless. It teaches us several powerful things precisely because it marks the failure of the classical theory. It tells us that collapse does not simply stop at some comfortable hidden core within general relativity. It tells us that event horizons do not merely hide stable, compressed matter forever in the classical picture. It tells us that extreme gravity forces the union of quantum mechanics and space-time geometry into the foreground. And it tells us that any final theory of nature must be able to say something coherent about conditions where general relativity predicts its own breakdown. There is also a conceptual lesson here about the difference between absence of access and absence of explanation. The event horizon cuts off direct observational access to the interior. That alone would make the black hole mysterious. But the singularity adds a second layer. Even if one could somehow bypass the observational barrier in a thought experiment, the classical explanation itself still fails in the deepest region. So the black hole interior is not merely hidden from us. In a crucial sense, it is hidden from the classical theory too. That is one reason black holes loom so large in theoretical physics. They do not just conceal things from telescopes, they expose incompleteness in the foundations. A singularity is nature's way of saying that the current categories are not enough. The same happened in a different way before quantum mechanics. Classical physics could not explain the stability of atoms, blackbody radiation, or the behaviour of matter at small scales. Those failures were not signs that the universe had become irrational. They were signs that a deeper framework was needed. The singularity may play a similar role for gravity. One of the more interesting questions is whether the singularity is truly located inside the black hole in the way we normally imagine, or whether that itself is too classical a notion. If space-time geometry emerges from some deeper quantum structure, then the singularity may be less like a destination and more like a marker of where the emergent description fails. That would mean asking what is at the singularity might be a bit like asking what lies north of the North Pole. The question uses familiar directional language beyond the domain where it still applies. In that case, the real task is not to find the object at the end, but to replace the framework that made the question sound sensible in the first place. There is also a psychological challenge here. Humans like objects. We like imagining things with size, shape, boundaries, and location. A singularity resists all of that. It is easier to picture a crushing point than to sit with the idea that the theory itself stops giving a physically interpretable picture. But scientific maturity often consists in tolerating exactly that kind of discomfort. We are not entitled to a visualizable answer. If the best current story ends in a breakdown, then breakdown is the answer for now. That said, there have been many imaginative attempts to think past the singularity. Some speculative ideas suggest that what looks like a singular collapse from one side might connect to the birth of a new region of space-time. Others propose that black hole interiors might be linked, under quantum descriptions, to entirely different structures than classical space-time suggests. These ideas are interesting and worth studying where they are mathematically serious, but they should not be mistaken for established fact. The honest state of play is that singularities are where our classical map ends, and the correct quantum continuation remains unresolved. It is worth remembering too that singularities are not unique to black holes in relativity. The standard cosmological model, when followed backward classically, also leads to a singular beginning. The early universe presents a similar message. General relativity gives a powerful account of expansion and cosmic history, but pushed all the way back, it appears to reach a boundary where the theory cannot continue cleanly. This parallel is important. Singularities are not weird decorative features of a few exotic objects. They are signals that classical space-time descriptions may have deep limits both at the birth of the universe and in the death of collapsing stars. In that sense, black hole singularities and cosmological singularities may be related clues pointing toward the same missing theory. Whatever finally replaces the singularity in a black hole may also help explain what replaces the classical beginning of the universe. This is part of why black holes matter far beyond their immediate astrophysical drama. They may be laboratories, at least theoretically, for the deepest questions about space-time itself. Another thing the singularity forces us to confront is how much of our current picture depends on separation between inside and outside, before and after, geometry and information. Near the singularity, these distinctions may no longer remain clean. If the very notion of smooth space-time fails there, then asking where the information is stored or how matter is arranged may require concepts that do not look like storage or arrangement in the usual sense. The paradoxes we discussed earlier may be telling us that the singularity is not just a technical flaw in the centre of the black hole, but a sign that our entire space-time-based description needs revision at the most fundamental level. And yet, despite all of this, the singularity is not where the black hole story stops being physically fruitful. quite the opposite. The fact that black holes seem to contain a region where classical gravity breaks down has inspired some of the most productive work in theoretical physics over the last several decades. Questions about entropy, horizons, information, quantum entanglement, holography, and emergent spacetime have all been sharpened by black holes. The singularity is a problem, but it is also a guide. It tells us where to look if we want to understand what the next layer of physics must accomplish. There is something almost ironic in that. The darkest objects in the universe, defined by regions from which light cannot escape, have illuminated some of the brightest conceptual issues in modern science. And the singularity, which looks at first like an admission of failure, may turn out to be one of the most valuable clues we have. It is the place where our current theories stop agreeing with our desire for completeness, and that very tension is often how physics advances. So when we say the singularity is where physics begins to break, we're not saying that nature becomes magical, arbitrary, or beyond reason. We're saying that classical general relativity, extraordinary though it is, points toward a region where it can no longer be the full story. The singularity is the classical endpoint of collapse, the future boundary inside the black hole, and the place where curvature is driven beyond the theory's capacity to remain sensible. It is not a tidy answer. It is the sharpest question mark inside the black hole. And once that is clear, something important follows. If the classical interior ends not in a satisfying physical picture but in a breakdown, then black holes cannot be understood only as eternal traps with hidden crushing centers. They must also be understood as quantum objects with temperature, entropy, and slow, long-term evolution. In other words, to move past the singularity as a mere stopping point, we have to step back and look at the other side of the black hole story, the side where even these darkest objects are not perfectly black, and where time gives them an unexpectedly slow way of dying. That shift changes the mood of the whole story, because for most of the last century, black holes were treated as the ultimate one-way destinations. Matter could fall in, light could fail to escape, time and space could be bent past ordinary understanding, information could become a crisis for theory, and somewhere in the interior classical physics could run into a singularity and stop giving clear answers. In that older picture, a black hole seemed like the perfect cosmic prison, an object that only grew, only consumed, and never gave anything back. Then Stephen Hawking showed that this picture was incomplete. When quantum theory is taken seriously in the curved space-time around a black hole, the black hole is not perfectly black after all. It emits radiation, very faintly, very slowly, but genuinely. And that single fact changed black holes from eternal sinks into thermodynamic objects. They have temperature, they have entropy, they can lose energy, they can shrink. Given enough time, they can die. That is one of the most startling reversals in all of physics. The very objects once defined by the impossibility of escape turn out, in a deeper quantum sense, to leak. Not by spraying out the same light that fell in, not by opening some hidden exit, but by emitting radiation as a consequence of quantum fields living in the strange geometry near the horizon. A black hole, which classical gravity treated as a perfect absorber, becomes in quantum theory a very patient emitter. At first glance, this sounds almost absurd. If not even light can escape from inside the event horizon, how can radiation come out at all? The key is that Hawking radiation is not best imagined as something climbing out from deep inside the black hole in defiance of the rules. The radiation is associated with the quantum behavior of fields near the horizon, not with ordinary matter making a heroic break for freedom from the interior. The black hole is not violating its own definition. It is revealing that the vacuum near a horizon is more complicated than classical intuition allowed. This is where the explanation often becomes both famous and a little dangerous. Many popular accounts describe Hawking radiation using a picture of particle pairs appearing spontaneously near the horizon. One particle falls in, the other escapes, and the escaping one becomes the radiation we observe. This image is useful to a point, and it has helped generations of people get their first grip on the idea. but it's not the full story, and taken too literally it can mislead. Quantum field theory in curved space-time is more subtle than little marbles popping into existence at the edge of a hole. Still, as a first rough picture, it captures something important. The horizon changes what counts as empty space, and the result is that the black hole can be associated with a flow of outgoing radiation. A more careful way to say it is this. In quantum theory, what one observer calls empty space is not always exactly what another observer calls empty space, especially in curved space-time or accelerating frames. Near a black hole, the geometry around the horizon affects the quantum fields in such a way that a distant observer sees a thermal spectrum of radiation coming from the black hole. That radiation carries energy away. Since energy and mass are linked, the black hole loses mass in the process. So the black hole gradually evaporates. The word evaporates is surprisingly apt. It makes the process sound almost gentle, which compared with supernovas and tidal destruction it certainly is. Black holes do not explode into nothing the moment this radiation appears. They very slowly lose mass over extraordinary lengths of time. For black holes formed from dying stars, the timescales are so enormous that every familiar human unit of duration becomes almost comically inadequate. These objects do not live for millennia, or even for the current age of the universe. They live vastly longer than that. A stellar mass black hole will take a period of time so immense to evaporate that writing the number down is more of a mathematical exercise than a practical description. This slowness is essential because it means Hawking radiation is not something astronomers directly observe from ordinary astrophysical black holes in any simple way today. The effect is far too weak. A black hole with the mass of a star is colder than the surrounding universe and absorbs more radiation from the cosmic environment than it emits through Hawking radiation. A supermassive black hole is colder still, absurdly so. These black holes are not yet in their dying phase in any practical sense. At the moment, the universe is too warm and too busy. The black holes are still net gainers, not net losers. That detail often surprises people, because once they hear that black holes evaporate, they imagine a fairly active process already underway. In truth, for the large black holes we know, Hawking radiation is more like a whisper than a shout. The bigger the black hole, the colder it is. That is one of the wonderfully backward features of black hole thermodynamics. In ordinary life, larger hot objects may feel as though they should contain more heat, in a straightforward way. Black holes refuse to follow that intuition. A more massive black hole has a lower temperature. A smaller black hole has a higher temperature. So as a black hole loses mass, it gets hotter, and as it gets hotter, it radiates more strongly. Its death is not a steady fade, but an acceleration. This inverse relationship between mass and temperature is part of what gives black hole evaporation its peculiar rhythm. A large black hole radiates faintly and changes very little over incomprehensible stretches of time. But if one somehow becomes small enough, the radiation grows stronger. The black hole loses mass faster. The temperature rises further. The final stages become increasingly intense. So the life of a black hole is dominated by long, quiet persistence, followed much later by a more rapid terminal phase. There is a kind of dark comedy in that, because black holes spend most of their existence with a reputation for voracious appetite while secretly being among the most patient slow burners in the cosmos. Given the age of the universe so far, none of the familiar astrophysical black holes have had anything like enough time to evaporate away through Hawking radiation. They are still in the vast early part of their lives if one thinks in those terms. Their eventual deaths belong to a universe far older, darker, and emptier than the one we currently inhabit. This brings us to the remarkable connection between black holes and thermodynamics. Before Hawking radiation, Jacob Bekenstein had already argued that black holes should have entropy, a measure of the number of possible microscopic states hidden behind their simple, exterior description. That idea was inspired partly by the information problem and partly by the analogy between black hole behavior and the laws of thermodynamics. Black holes seem to obey something like a second law. The area of their event horizons never decreased in classical processes, much as entropy in a closed system tends not to decrease. At first, this looked like a suggestive analogy. Hawking radiation made it real. If black holes radiate with a temperature, then they truly are thermodynamic objects. The analogy becomes a physical identity. This was a major conceptual leap. It meant that gravity, quantum theory, and thermodynamics were all entangled in black holes. A black hole is not just a region of curved space-time. It is also an object with entropy proportional to the area of its horizon. That is an odd and profound fact. Most familiar systems have entropy that scales more naturally with volume. Black holes tie entropy to surface area, which helped inspire later ideas about holography and the deep relationship between information and boundaries. In a sense, the black hole horizon behaves less like a passive border and more like a bookkeeping surface for hidden microscopic possibilities. That idea still feels radical, and perhaps it should. It suggests that black holes are not merely where things vanish, but where the universe stores and organizes information in a way that rewrites ordinary expectations about space. The entropy of a black hole is enormous, which means that even though the outside description looks simple, the internal or microscopic accounting behind that simplicity must be vast. A black hole may appear bald from far away, but thermodynamically it is carrying an extraordinary hidden complexity. Now, when Hawking radiation carries energy away, what exactly is being emitted? In the simplest treatments, the radiation has a thermal character. That means it resembles the sort of emission associated with temperature rather than with the detailed identity of the matter that originally formed the black hole. A hot stove radiates because it has temperature, not because it remembers the biographies of the people who built it. Hawking radiation, in its original description, behaves in that kind of universal way. And that is precisely why it generated the information paradox. If the radiation is purely thermal, then the black hole seems to forget the details of what fell in. That brings us back to the earlier tension. If black holes evaporate completely into apparently thermal radiation, and if the detailed information about what formed them and fed them is not encoded in that radiation, then the universe seems to lose information. So Hawking radiation is not just the mechanism by which black holes die, it is the mechanism that forces the paradox into the open. Without evaporation, one might imagine information hidden forever behind the horizon. With evaporation, the hiding place itself disappears. The question becomes unavoidable. If the black hole is gone, where did the information go? Many modern approaches suggest that the radiation is not truly featureless in the final accounting. The outgoing quanta may contain subtle correlations built up over the life of the black hole that preserve information in an extremely scrambled form. But even if that is the correct broad picture, the practical character of Hawking radiation remains astonishingly impersonal. A black hole does not appear to emit back out a recognizable stream of everything it swallowed in an orderly archive. It radiates with the patient indifference of a thermal object, and only in the deepest quantum description may the fine details be recoverable in principle. The word principle does a great deal of work there. In principle, the information may survive. In practice, reconstructing it from Hawking radiation would be so difficult that the phrase impossible for all useful purposes would be generous. Imagine trying to recover the full details of every object ever dropped into a black hole by analysing a hugely extended, incredibly subtle radiation field emitted over fantastically long times. It would make assembling a shattered vase from volcanic ash look refreshingly manageable. There is also an important cosmic timing issue. Black holes cannot begin their final evaporation era in earnest until the universe around them becomes colder than they are. At present, the cosmic microwave background and other surrounding radiation fields bathe the universe with a faint thermal glow. Large black holes are colder than this background, so they absorb more than they emit. Only after the universe expands and cools far more will astrophysical black holes become net evaporators. This means the true age of black hole evaporation belongs to the distant future of cosmology, not to the current epoch of stars and galaxies as we know them. That future is almost impossibly remote. Long after stars have stopped forming, long after galaxies have aged and dimmed, long after familiar structures of luminous matter have decayed or dispersed. In that far future, black holes may be among the last major objects still shaping the universe. Their evaporation becomes part of the final long cooling of cosmic history. The universe that witnesses black holes die will not look anything like the present one. It will be darker, emptier, quieter, and governed by processes so slow that even patience as a concept begins to feel overmatched. Yet despite the vastness of those timescales, the logic is simple. A black hole with a finite temperature emits radiation. Emitting radiation costs it energy. Losing energy reduces its mass. Reduced mass raises its temperature. Raised temperature increases emission. The black hole lives by losing what once defined it. The most famous absorber in physics turns out to contain the seeds of its own eventual disappearance. One might wonder whether the final evaporation ends in a neat vanishing act or in some more complicated terminal event. The honest answer is that our confidence weakens as the black hole becomes extremely small. Hawking's calculation is robust for large black holes, where the spacetime curvature near the horizon can be treated in a semi-classical way, meaning quantum fields are considered on a classical gravitational background. But when the black hole shrinks enough, quantum gravity effects are expected to become important. At that stage, we do not yet have a complete final theory. So while the broad story of slow evaporation is solid, the exact last instant or last phase remains uncertain. Does the black hole disappear completely? Does it leave a remnant? Does the information emerge in some final burst? That remains part of the deeper unresolved problem. This is a good example of how black holes repeatedly do the same thing to physics. They begin with a clean and terrifying idea, then reveal a deeper quantum subtlety, then finally pushes into a regime where our current framework runs out. Hawking radiation does not solve every mystery. It opens a new one. It teaches us that black holes are thermodynamic and mortal, but it also forces us to ask how evaporation is reconciled with information preservation, and what a full quantum gravity description of the end must look like. There is another lesson hidden in the very existence of Hawking radiation. It tells us that empty space is not empty in the naive classical sense. Quantum fields are always there, even in vacuum. The black hole horizon is not an inert border surrounded by featureless nothing. It is embedded in a quantum world that responds to curvature and causal structure. That means black holes are not isolated from the deep quantum fabric of the universe. They are among the clearest places where that fabric becomes impossible to ignore. And because Hawking radiation depends on the observer and on the way quantum fields are defined relative to the curved geometry, it also deepens the strange relationship between observation and reality in black hole physics. The black hole is not simply a dark object with a leak. It is a region where what counts as vacuum, particle, temperature and emission depends on how quantum theory and spacetime geometry are stitched together. This is not a flaw in the science, it is the science. It is what makes black holes such powerful meeting points for ideas that elsewhere can remain politely separate. The phrase slowly die therefore carries more meaning than it first appears to. Black holes die not because some external force tears them down, but because the combined logic of gravity and quantum theory refuses to let them remain perfectly sealed forever. Their death is written into the horizon itself once the quantum world is allowed to speak. A black hole may seem like the most final object imaginable, but even it is temporary. That is a remarkable thought. In a universe where mountains erode, stars exhaust their fuel, atoms can decay, and galaxies collide, even black holes are not exempt from change. There is something deeply revealing in that. Black holes are often described as the ultimate endpoints of collapse, the places where matter is carried past return, and classical theory breaks down. Yet they are also finite thermodynamic systems with temperatures and lifetimes. They are both endings and processes, both traps and emitters, both hidden and revealing. Hawking radiation is what forces us to hold those truths together. It tells us that a black hole is not merely the graveyard of matter, it is part of the ongoing evolution of the universe, participating in the long arithmetic of energy and entropy. And once you allow that, the story changes again. Because if black holes can form from stars, swallow matter, challenge information theory, hide singularities behind horizons, and then spend unimaginable ages radiating themselves away, then they are no longer just exotic side characters in the cosmic narrative. They become mirrors for some of the deepest questions we can ask about law, time, knowledge, and the structure of reality itself. Which is where the last part of this journey naturally begins to take shape, not with another mechanical detail of what black holes do, but with what they have already taught us about the universe, and about the peculiar kind of creatures who keep staring into the dark and insisting on asking what is really there. And once the story reaches that point, it becomes clear that black holes are not interesting only because they are extreme. Plenty of things in the universe are extreme. Some stars are unimaginably hot. Some explosions release more energy in a moment than our sun will produce over its entire lifetime. Galaxies collide, space expands, atoms hum with hidden structure. The universe is not short on dramatic behaviour. What makes black holes different is that they force several of our deepest ideas to meet in one place, and then refuse to let them sit comfortably together. A black hole begins with gravity, but it does not stay there. Follow it carefully and you end up talking about time, light, motion, thermodynamics, entropy, information, quantum fields, and the limits of knowledge itself. It is a single object, or rather a single kind of object, that behaves like a pressure test for nearly everything fundamental. That is one of the first things black holes reveal about the universe. The universe is not divided into neat departments in the way we sometimes teach it. Gravity does not live in one tidy corner. Time does not mind its own business elsewhere. Matter, energy, geometry, temperature, and information are not separate stories with clear office doors and polite scheduling. In the deepest places, they all turn out to be entangled. That is not just a technical lesson for physics, it is a broader lesson in how reality seems to be built. The world is not arranged according to the categories most convenient to human thought. We like separate boxes because separate boxes are manageable. We like saying this is space, this is time, this is matter, this is heat, and this is information, as if the universe were designed by a very organised librarian. Black holes keep showing us that the categories blur when conditions become extreme enough. Heat turns out to matter for gravity. Information turns out to matter for horizons. Space and time stop behaving like independent ideas. The lesson is not that the universe is chaotic. The lesson is that it is more unified, and therefore more difficult, than our first pass at it suggests. Black holes also reveal that invisibility is not the same as absence. This is one of the most concrete things they teach. We cannot see a black hole directly in the ordinary way because no light escapes from inside the horizon. And yet we know black holes are there. We know because stars orbit invisible masses. We know because gas heats and spirals. We know because light bends. We know because gravitational waves ripple across space when black holes merge. Science in this sense is not simply looking harder. It is learning how to read consequences. It is learning that some of the most real things in the universe are known not by direct view, but by disciplined inference. That is a useful correction to ordinary intuition, because in everyday life seeing often feels like the final court of appeal. If something is visible, it feels real. If it is not visible, it feels less settled. Black holes remind us that this is a human habit, not a law of nature. The universe does not owe us transparency. It does not promise to present itself in forms convenient to eyes that evolve to find fruit, avoid cliffs, and keep track of each other in daylight. Sometimes reality must be reconstructed from traces. Sometimes the most certain things are things we have never seen directly, only understood through their effects. In that way, black holes reveal something about science itself. Science is often described as a collection of facts, but it is just as much a disciplined method of humility. It is a way of saying, the universe may not look how we expect, and our instincts may not be enough, so let us build better ways of asking. That is exactly what black hole research has required. No one discovered black holes by stumbling into one and filing a practical report afterward. We discovered them by following equations, predictions, observations, and consequences further than common sense was comfortable going. In other words, black holes reveal that one of humanity's most unusual abilities is the willingness to trust careful reasoning, even when it leads us somewhere imagination cannot easily walk. There is another lesson there, and it is perhaps even more intimate. Black holes reveal that human curiosity is not limited to what helps us survive the afternoon. On a strict survival basis, one could argue that our species might have done perfectly well without ever learning what happens near an event horizon. It does not help much with grocery lists, shoe repairs, or choosing a pleasant soup, and yet we care. We care enough to build telescopes, detectors, computers, and theories. We care enough to spend generations refining ideas that may only pay off in understanding, not in immediate comfort. There is something distinctly human in that. We do not only solve the problems placed directly in front of us, we also lean toward the remote, the difficult, and the invisible. Black holes reveal this by being so wildly beyond our natural scale. They are not like mountains, storms, or animals, things our ancestors could meet and learn about face to face. Black holes cannot be approached in any ordinary sense. They belong to distances, masses, and times far beyond direct human experience, and still we insist on thinking about them. That insistence says something important about us. We are a species that can live on one small planet and yet become intellectually involved with the fate of stars, the geometry of space-time, and the eventual evaporation of objects we will never touch. That is not a practical instinct in the narrow sense. It is something stranger and richer. It is the instinct to understand. At the same time, black holes reveal the limits of that instinct. They show us how far reason can go, and also where it currently stops. This may be one of their most valuable gifts. When general relativity carries us to the event horizon and into the interior, it works beautifully. When Hawking radiation brings quantum fields into the picture, the theory opens further. But at the singularity and in the information paradox, our frameworks collide or break. Black holes are therefore reminders that understanding is not the same as completion. We can know a great deal and still stand in front of unanswered questions. We can have equations that work magnificently and still face a deeper theory not yet in hand. That is not failure. That is simply what serious knowledge looks like. This is worth saying clearly, because there is a common temptation to imagine that science advances by replacing mystery with certainty until, one day, all the important questions are used up. Black holes make it obvious that the real process is more interesting than that. Often, the better we understand something, the sharper the remaining mystery becomes. Black holes were once thought to be little more than odd gravitational sinkholes in the mathematics of relativity. Then they became plausible astrophysical objects, then observed ones, then thermodynamic systems, then central players in the problem of information and quantum gravity. Each improvement in understanding did not remove mystery so much as refine it. Black holes reveal that genuine understanding often deepens the question. They also reveal that the universe is lawful even when it is strange. This may sound like a small point, but it matters. Much of what makes black holes unsettling is that they violate our intuition. Time does not behave as expected. Escape changes meaning. Horizons are real without being solid surfaces. Singularities arise as limits of theory. Yet none of this happens at random. Black holes are not pockets of cosmic mischief where the rules are suspended. Quite the opposite. They are where the rules are followed so exactly, and with such severe consequences, that our everyday expectations fail. This is a profoundly important lesson about nature. Reality is not obligated to be intuitive. only consistent. That has a calming side as well as a disturbing one. It means that even the most alien parts of the universe are not beyond thought. They may be beyond ordinary imagination, but not beyond disciplined inquiry. The universe does not transform into nonsense just because it becomes difficult. Black holes reveal that the same lawful structure governing apples, planets, and clocks can also govern horizons, tidal destruction, and thermal death. Strange does not mean irrational. Difficult does not mean unknowable. It only means that human intuition must be trained, corrected, and sometimes overruled. Black holes also tell us something about scale and importance. In ordinary life, we often assume that what is central must be visible, active, and obvious. But black holes are often central precisely by being hidden. The supermassive black holes at the centres of galaxies can help shape their environments profoundly. They influence the behaviour of surrounding matter, the growth of structures, and in some cases the history of star formation through the energy released in the regions around them. The dark object at the heart of a galaxy may quietly help regulate the life of the whole system. This is a useful correction to the idea that power must always look loud. In the universe, some of the most influential things are invisible until you notice what moves because of them. That pattern extends beyond astronomy. It is one of those places where black holes can reveal something about ourselves without resorting to any mystical language. Human life, too, is often organised by forces that are not directly visible. Memory, expectation, fear, habits, grief, affection, time itself. None of these are objects sitting on a table, yet they shape the paths we take. Black holes are not metaphors for those things, and it is usually best not to push scientific ideas into sentimental work they did not volunteer for. But it's fair to say that studying black holes can sharpen our respect for unseen structure. Not everything important announces itself directly. Some things are known by the way they bend the rest. There is also a lesson in simplicity. Black holes are among the simplest macroscopic objects in the universe from the outside. They are described by surprisingly few properties, and yet that simplicity hides extraordinary complexity and unresolved depth. This reveals something interesting about nature. Simplicity at one level does not guarantee simplicity underneath. A black hole looks stripped down in its external description, but it leads us straight into entropy, microscopic states, information puzzles, and the possible emergence of spacetime from deeper quantum structure. The plain exterior is not the end of the story, it is the beginning of a harder one. Humans, too, tend to overvalue surfaces. We are quick to assume that what looks simple is simple, that what looks settled is settled, that what does not display complexity cannot contain it. Black holes expose the weakness of that assumption in the most severe possible terms. The universe may package its deepest difficulties inside very economical forms. A dark sphere with a horizon sounds almost minimalist. It turns out to be an intellectual trapdoor beneath half of modern theoretical physics. Then there is the matter of time. Black holes reveal, more clearly than almost anything else, that time is not the universal steady flow our instincts want it to be. Near them, clocks disagree dramatically. From different viewpoints, the same process can look stretched, delayed, or completed. Inside them, the relation between time and inward motion becomes deeply unfamiliar. This does not only tell us something technical about relativity, it reveals that one of the most intimate features of our experience, the sense that time just passes the same way everywhere, is a local convenience rather than a universal truth. That can be destabilizing, but it can also be clarifying. We tend to treat time as a background resource we spend, save, waste, and run out of. Black holes remind us that time is part of the physical world, not just a mental calendar pinned behind it. It bends. It depends on gravity and motion. It shapes causality. It is not merely the stage on which events occur, it is part of the event. That is a difficult thing to absorb fully because human life runs on schedules, routines, and clocks that flatten this deeper truth into something manageable. But the black hole will not let us keep flattening forever. Black holes also reveal that endings in the universe are rarely simple endings. A star collapses and forms a black hole, but in doing so it may blast heavy elements into space. A black hole swallows matter, but the surrounding accretion process can light up whole regions and reshape galaxies. A black hole seems like a final trap, yet Hawking radiation means even it has a long future and an eventual death. This is a recurring pattern in astrophysics. Birth and death are not clean opposites. Destruction is often entangled with creation. Collapse can seed structure elsewhere. Finality is often only final from one point of view. That too is useful to notice. Human beings are fond of simple endings. We like neat boundaries between beginning and conclusion, success and failure, growth and collapse. The universe is less cooperative. It tends to recycle consequences. The death of a star can become the raw material for planets. The collapse into a black hole can trigger radiant phenomena around it. The evaporation of a black hole belongs to the very long thermodynamic future of the cosmos. Black holes reveal that even the most severe-seeming endpoints are often embedded in larger processes. Perhaps most of all, black holes reveal that the universe is under no obligation to be comforting, but it may still be understandable. That is a very mature kind of good news. A black hole does not care whether a horizon feels unfair or whether singularities make us uneasy. Nature is not arranged for reassurance. Yet the fact that we can understand so much of such an alien object at all is extraordinary. We can predict the formation of black holes, detect their mergers, measure their masses, map the behavior of matter around them, calculate their thermodynamic properties, and argue in technical detail about the fate of information in their evaporation. That is not a small achievement. It is one of the clearest signs that human reason, though limited, is astonishingly capable when paired with patience and evidence. And patience is another thing black holes reveal about us. To study them, we have had to work on timescales larger than individual careers. Ideas proposed by one generation are tested, refined, challenged, and extended by the next. Observations once impossible become routine decades later. The first discussions of black holes as serious physical objects came long before the instruments existed to examine them in detail. Hawking radiation was predicted long before any imaginable direct detection from astrophysical black holes was practical. The story of black holes is therefore also a story about intellectual endurance. We are willing, at least sometimes, to keep asking a question long after the first excitement has passed. That is a rather beautiful thing about science, though beautiful in a sturdy practical way rather than a dreamy one. It shows that human beings are capable of sustained attention to reality. Not always, certainly. We are also wonderfully distractible, alarmingly tribal, and easy to interest in nonsense. But at our best, we can spend centuries on a question simply because the universe has not answered it yet. Black holes reveal that best version of us. They also sharpen a simpler kind of humility. No one gets to be casual around a black hole, not even the theory. Our ordinary instincts fail. Our language strains. Our best equations eventually announce their own limits. This is useful because humility in science is not self-doubt for its own sake. It is accuracy about scope. It is knowing what you know, what you infer, what you suspect, and where the map ends. Black holes force that honesty. If you speak about them carelessly, they expose the carelessness very quickly. If you oversimplify them too much, something important breaks. They demand precision, and that demand is healthy. At the same time, they reward imagination of the disciplined sort. Not fantasy, not speculation untethered from evidence, but imagination guided by mathematics, observation, and conceptual clarity. It took imagination to believe that collapsed stars could create horizons. It took imagination to ask what an outside observer would see. It took imagination to suspect black holes might radiate. It takes imagination now to build possible bridges between gravity, information, and quantum theory. Black holes reveal that science is not the enemy of imagination. It is the training of imagination so that it can survive contact with reality. And perhaps that is where they reveal something most personal. We are small creatures in a large universe. That fact is obvious enough. But black holes show that smallness and significance are not opposites. We are tiny compared with galaxies, fragile compared with stars, and brief compared with cosmological time. Yet we can understand enough to know that horizons exist, that time dilates, that information may be preserved in scrambled quantum form, and that objects millions or billions of times more massive than our sun slowly radiate themselves away over incomprehensible ages. Small creatures should not, by any obvious evolutionary logic, be able to think these thoughts. And yet here we are. So what do black holes reveal about the universe? They reveal a universe more interconnected than intuition expects, more lawful than fear suggests, more subtle than first theories imply, and more willing to hide its deepest workings inside simple exteriors than common sense would prefer. They reveal that space and time are dynamic, that information matters physically, that thermodynamics reaches into gravity, and that the darkest objects can illuminate the foundations of reality. And what do black holes reveal about us? They reveal that we are the sort of beings who ask what lies beyond visibility, that we can follow logic into places no body could go, that we can live ordinary lives under ordinary skies and still care about horizons, singularities, and the far future of evaporating stars. They reveal that curiosity is one of our strangest and most durable traits. They reveal that humility and ambition can coexist. And they reveal that even when the universe does not make itself easy, we continue to ask, to test, to revise, and to look again. So if you are listening now at the end of this long, quiet journey into black holes, perhaps that is the final practical thing to keep. A black hole is not only a place where matter falls and light fails, it is also a place where human understanding is stretched, corrected, and enlarged. We went looking for an object so extreme that it seemed almost beyond reason, and what we found instead was a mirror held up to reason itself. Not a perfect mirror, certainly. More the sort of mirror one finds in an old observatory after midnight, slightly warped, faintly unsettling, and unexpectedly honest. And wherever you happen to be listening from tonight, whether the hour is late and the room has gone still, or whether you are only borrowing a little silence from a busier day, I hope this has left you with the calmer version of awe rather than the noisy one. Not the feeling that the universe is impossible, but the feeling that it is deeper than it first appears and still open to thought. Black holes do not make the cosmos smaller, safer, or easier. They make it larger in the mind. And perhaps that is one of the quiet reasons we keep returning to them. Because in trying to understand what happens inside a black hole, we end up discovering something just as interesting about what happens inside us when we refuse to look away from a hard question.